Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep mathematics of space, where a single comet has quietly rewritten our understanding of the universe. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the darkness between stars, where temperature hovers 3 degrees above absolute zero, something moves. Not the familiar dance of planets around their stellar hosts, but the patient drift of ice and rock across distances so vast that light itself grows weary crossing them. This is 3I/Atlas, a visitor from the interstellar medium, carrying within its frozen nucleus the chemical signatures of alien star systems and the gravitational memories of encounters our models never predicted. The comet announces itself first as a smudge of light against the cosmic background radiation, detected by automated survey telescopes that scan the sky with mechanical precision. These instruments, scattered across Earth's surface like electronic sentinels, register photons that have traveled for months or years from the comet's slowly warming surface. The light carries information encoded in wavelengths, each absorption line telling stories of molecular bonds formed in the cold of space, far from any sun's warmth. Astronomers plot the visitor's trajectory with orbital mechanics equations that have served faithfully for centuries. Newton's laws, refined by Einstein's corrections for relativistic effects, should predict exactly where 3I/Atlas will travel as it falls toward our sun. Yet something in the mathematics refuses to cooperate. The comet's path curves through space in ways that standard gravitational theory cannot fully explain, as if invisible hands guide its journey through the solar system's gravitational architecture. The orbital elements, eccentricity, inclination, argument of periapsis, paint a picture of impossibility. 3I/Atlas approaches from a direction that suggests it has never been bound to our sun's gravity, never participated in the slow clockwork of planetary motion that has operated undisturbed for 4.5 billion years. Its hyperbolic trajectory speaks of origins in the vast spaces between stellar systems, where matter drifts in temperatures so cold that molecular motion nearly ceases entirely. Only 3 confirmed interstellar objects have ever crossed our solar system's boundary, each one rewriting textbooks with quiet persistence. Oumuamua came first, tumbling through space like a cosmic cigar, its surface reflecting sunlight in patterns that suggested composition unlike any asteroid or comet in our familiar celestial inventory. Then came 2I/Borisov, more traditionally comet-like, but carrying chemical signatures that pointed to formation around a different star entirely. Now 3I/Atlas arrives with its own peculiar mysteries, defying categorization with the same gentle stubbornness that characterizes all visitors from the deep. The comet's nucleus, perhaps 10 kilometers across, contains ice that formed in molecular clouds between the stars. Water molecules locked in crystalline structures that never knew the warmth of a stellar nebula, never participated in the collapse and heating that birthed our solar system. These ancient ices carry isotopic ratios that speak of nucleosynthesis in stellar cores that burned and died when the universe was younger. Their heavy elements forged in supernovae that scattered metals across interstellar space with violent generosity. As 3I/Atlas continues its approach, spectroscopic observations reveal absorption features that do not match any known terrestrial or solar system materials. The comet's reflected light passes through Earth's atmosphere and into spectrographs that spread the photons across arrays of detectors, each wavelength recorded with precision measured in angstroms. Yet among the familiar signatures of water vapor and simple organic compounds, there appear lines that correspond to molecular structures Earth's chemistry has never produced naturally. The mystery deepens as astronomers attempt to model the forces acting upon the visitor. Solar radiation pressure should accelerate the comet away from the Sun in predictable ways, creating the classic curved trajectory of objects falling through our star's gravitational well. But 3I/Atlas exhibits subtle deviations from these predictions, small accelerations that accumulate over time into significant changes in position. The comet appears to experience forces beyond those accounted for in standard celestial mechanics, as if the fabric of space itself carries additional complexity in regions where interstellar matter has traveled for eons. Ground-based observatories and space telescopes train their instruments on this enigmatic visitor, collecting photons that carry the comet's secrets across millions of kilometers of vacuum. Each observation adds data points to orbital calculations that grow increasingly complex as astronomers attempt to reconcile theory with observation. The mathematics that successfully predict the motion of every planet, moon, and asteroid in our solar system struggle to contain the gentle rebellion of 3Y/Atlas against gravitational orthodoxy. Perhaps most intriguingly, the comet's trajectory appears to carry it through regions of space where our theoretical models break down entirely. These are the zones beyond the Kuiper belt, where solar influence fades into the background radiation of the galaxy itself, where the boundary between our Sun's domain and the interstellar medium blurs into uncertainty. Here, in the cold darkness where comets from the Oort cloud occasionally begin their million-year journeys toward the inner solar system, 3I/Atlas moves with the confidence of an object that has never acknowledged such boundaries. The visitor brings with it the accumulated gravitational history of its journey across the galaxy. Every close encounter with massive objects, stars, brown dwarfs, dense molecular clouds, has left subtle imprints on its trajectory. Tiny deflections that compound over millions of years into the specific path that brought it to our solar system. These gravitational memories, encoded in orbital parameters, tell stories of stellar neighborhoods we will never visit, of cosmic environments where the laws of physics operate under conditions Earth has never experienced. As winter deepens across Earth's northern hemisphere, 3Y/Atlas continues its patient approach toward perihelion, the point of closest approach to our Sun. Solar heating will soon begin the process of sublimation, turning ancient ices directly into vapor without the intermediate phase of liquid water. This transformation will release gases that have remained frozen since before our solar system's formation, creating a temporary atmosphere around the comet that will scatter sunlight and create the familiar tail that makes comets visible to human observers. But even in this most familiar aspect of cometary behavior, 3I/Atlas promises to surprise. Its composition, forged in the cold of interstellar space under conditions that differ subtly from those in our solar nebula, may produce outgassing patterns unlike anything astronomers have previously observed. The visitor from the void approaches with secrets locked in ice, carrying within its nucleus the potential to quietly revolutionize our understanding of how matter behaves in the deep spaces between stars. The mathematics begin to break down in the pre-dawn hours when astronomers review the latest astrometric measurements. Position data collected over weeks of observation should converge into clean orbital solutions, elegant equations that describe 3I/Atlas's path through space with the precision that has characterized celestial mechanics since Kepler first mapped planetary ellipses. Instead, the numbers refuse to settle into familiar patterns. Each new observation adds uncertainty rather than clarity, as if the comet operates according to gravitational rules that exist somewhere beyond the comfortable boundaries of Newtonian physics. Doctor. Sarah Chen sits before arrays of computer monitors in the dim glow of Mauna Kea Observatory's control room, watching orbital fitting algorithms struggle with data that should be routine. The software cycles through thousands of potential solutions, each iteration attempting to find mathematical harmony between theoretical predictions and observed reality. Numbers cascade across screens in endless streams: right ascension, declination, proper motion vectors, all refusing to coalesce into the stable orbital elements that would allow precise prediction of the comet's future position. The problem reveals itself most clearly in the residuals, those tiny differences between where 3I/Atlas should appear and where telescopes actually find it. In normal celestial mechanics, these residuals shrink towards zero as observations accumulate and orbital solutions improve. For 3I/Atlas, they persist with stubborn consistency, suggesting that some fundamental assumption about the comet's motion requires revision. The visitor from interstellar space appears to experience accelerations that standard models cannot account for, as if additional forces act upon its nucleus with gentle but inexorable persistence. Gravitational perturbations from the giant planets should be entirely calculable. Jupiter's massive influence reaches across astronomical units, its gravity wells and resonances mapped with extraordinary precision through centuries of observation. Saturn, Uranus, and Neptune add their own subtle contributions to the cosmic choreography, their positions known to within kilometers at any given moment. Yet when astronomers include all these influences in their calculations for 3I/Atlas, discrepancies remain. The comet follows a path that seems to acknowledge these gravitational giants while simultaneously obeying additional rules that Earth's physics has not yet discovered. The orbital eccentricity presents its own mathematical puzzle. 3I/Atlas exhibits a hyperbolic trajectory with an eccentricity greater than unity, confirming its origin beyond our solar system's gravitational boundary. But the precise value of this eccentricity shifts slightly with each observation, as if the comet's fundamental relationship to our sun's gravity evolves during its approach. This behavior challenges the conservation laws that form the foundation of orbital mechanics, suggesting that energy and angular momentum may not remain perfectly constant for objects carrying the gravitational memories of interstellar journeys. Temperature calculations add another layer of complexity to the mathematical rebellion. As 3I/Atlas approaches the Sun, solar radiation should heat its nucleus according to well-established thermodynamic principles. The comet's surface temperature should rise predictably with decreasing heliocentric distance, following inverse square law relationships that govern all radiation in space. Yet spectroscopic observations suggest heating patterns that deviate from these simple models, as if the comet's material responds to solar energy in ways that Earth's chemistry has never exhibited. The visitor's albedo, its ability to reflect rather than absorb solar radiation, proves equally enigmatic. Most comets darken as sublimating ices expose underlying rocky material, creating surfaces that absorb more sunlight and accelerate the outgassing process. 3I/Atlas maintains a reflectivity that changes in unexpected ways, sometimes brightening when models predict it should darken, sometimes maintaining constant brightness despite significant changes in solar heating. This behavior suggests surface composition unlike anything in our familiar cometry catalog. Rotational dynamics provide yet another mathematical mystery. The comet's brightness varies periodically as it tumbles through space, creating a light curve that should reveal the nucleus's rotation period and approximate shape. For most comets, this analysis yields clean sinusoidal patterns that correspond to irregularly shaped objects spinning around their shortest axis. 3I/Atlas produces light variations that resist such simple interpretation, exhibiting complexity that suggests either highly unusual shape or rotational behavior that differs from standard, rigid body dynamics. Perturbation analysis reveals the most troubling aspects of the mathematical breakdown in classical celestial mechanics. Small forces acting over long periods produce cumulative effects that can be calculated precisely. Solar radiation pressure, for instance, creates tiny accelerations that push cometary material away from the Sun, producing measurable changes in orbital elements over time. The Yarkovsky effect adds thermal recoil forces as rotating objects radiate heat into space, creating subtle accelerations that accumulate over years of observation. For 3I/Atlas, these well-understood perturbations fail to account for the observed orbital changes. The comet exhibits non-gravitational accelerations that exceed predictions based on standard outgassing models and radiation pressure calculations. Something else influences its motion through space, some additional force or effect that operates beyond the comfortable boundaries of established physics. The mathematical models that successfully describe every other object in our solar system encounter their limits when confronted with this visitor from the interstellar void. Integration methods used to propagate orbital solutions forward in time become unstable when applied to 3I/Atlas, numerical algorithms that maintain precision for centuries when calculating planetary positions develop growing uncertainties within months for this interstellar visitor. The mathematical chaos that characterizes some asteroid orbits near gravitational resonances appears to affect 3I/Atlas, even in regions of space where perturbations should be minimal and predictable. Statistical analysis of the orbital uncertainties reveals patterns that challenge conventional error propagation theory. Measurement uncertainties should decrease as observations accumulate, following well-established statistical principles that govern all astronomical data reduction. Instead, certain components of 3I/Atlas's orbital solution maintain persistent uncertainties that refuse to shrink despite increasingly precise astrometric measurements. The comet appears to inhabit a state of fundamental unpredictability that resists the mathematical tools astronomers use to tame cosmic motion, barycentric coordinates, which reference positions relative to the solar system's center of mass, provide no relief from the mathematical mysteries. Even when accounting for the subtle motion of the Sun itself as it orbits the common center of mass with Jupiter and the other planets, 3I/Atlas maintains orbital peculiarities that standard reference frame transformations cannot resolve. The visitor's motion appears fundamentally different from objects that have spent billions of years bound to our star's gravitational influence. The comet's approach trajectory suggests origins in specific regions of interstellar space, where our understanding of gravitational environments remains incomplete. Dense molecular clouds, regions where star formation actively redistributes mass and energy, could have influenced 3I/Atlas during its long journey between stellar systems. These environments contain gravitational complexities that Earth-based astronomy has never directly observed, potential sources of the mathematical discrepancies that characterize this enigmatic visitor. As autumn transitions toward winter, astronomers continue their patient struggle with equations that refuse to behave. The mathematics of 3I/Atlas's arrival challenge fundamental assumptions about how objects move through space, forcing quiet revisions to theories that have served reliably for centuries. In observatories around the world, computers work through the endless iterations of orbital calculations, seeking mathematical harmony that may require entirely new physics to achieve. The visitor from the void approaches with gentle persistence, carrying within its trajectory the seeds of scientific revolution wrapped in the deceptive simplicity of ice and rock drifting through the cosmic dark. In the vast computational networks that span continents, where supercomputers process petabytes of astronomical data with relentless precision, a quiet rebellion spreads through the algorithms designed to predict celestial motion. The orbital integration software that successfully models every planet, moon, and asteroid in our solar system encounters something unprecedented when it attempts to chart 3I/Atlas's future path. The comet's trajectory passes through what theorists now call forbidden zones, regions of space where our mathematical models break down entirely, where the comfortable certainties of Newtonian mechanics give way to something far more mysterious. These zones exist primarily in the conceptual realm, defined not by physical boundaries, but by the limits of human understanding. They occupy the spaces between what we know and what we suspect, the mathematical territories where equations become unstable and predictions dissolve into uncertainty. For 3I/Atlas, these forbidden regions lie scattered along its trajectory like invisible reefs in an ocean of seemingly empty space, each one marking a point where our theories must acknowledge their own incompleteness. The first forbidden zone emerges at approximately 18 astronomical units from the Sun, well beyond the orbit of Saturn, but still within the theoretical sphere of solar influence. Here, gravitational models begin producing wildly divergent results depending on which computational approach astronomers employ. Classical n-body integration methods suggest one trajectory, while general relativistic calculations predict another. Modified Newtonian dynamics proposed to explain galactic rotation curves without invoking dark matter, yields a third possibility entirely. The comet's actual path appears to thread between these predictions with mathematical precision that none of them can fully capture. Dr. Eleanor Vasquez, working through another sleepless night at the European Southern Observatory's Data Processing Center, watches her screens fill with error messages as orbital propagation algorithms encounter numerical instabilities they were never designed to handle. The software, refined through decades of successful solar system modeling, simply cannot maintain computational stability when tracking 3I/Atlas through these regions of theoretical uncertainty. Integration steps that should remain constant begin varying wildly, as if time itself becomes unreliable in the comet's vicinity. The mathematical breakdown manifests most clearly in the Hamiltonian formulation of celestial mechanics, where energy and angular momentum should remain perfectly conserved throughout any gravitational encounter. For 3I/Atlas, these fundamental conservation laws appear to develop small but persistent violations that accumulate over time. The discrepancies remain well within observational uncertainties for now, but their systematic nature suggests that something about the comet's interaction with space-time operates beyond the framework of classical physics. Perturbation theory, the mathematical foundation for understanding how small forces create large changes over astronomical timescales, reaches its limits when applied to 3I/Atlas's motion through these forbidden zones. The standard approach involves expanding the gravitational potential in series of spherical harmonics, each term representing increasingly subtle effects from planetary masses and solar system structure. For this interstellar visitor, the series refuses to converge, producing mathematical expressions that grow without bound rather than approaching stable solutions. The comet's passage through the heliopause region, the boundary where solar wind meets interstellar medium, creates computational challenges that expose fundamental gaps in our understanding of this transition zone. Current models treat the heliopause as a relatively simple boundary layer where charged particles from our Sun encounter the neutral interstellar medium. But 3I/Atlas's behavior suggests this region contains gravitational complexities that Earth-based physics has never directly confronted. The visitor's trajectory bends in ways that suggest interaction with mass distributions that remain invisible to our instruments. Plasma physicists studying the solar wind's interaction with interstellar space find their magnetohydrodynamic models struggling to account for 3I/Atlas's electromagnetic signature. The comet should interact with the solar wind's magnetic field in predictable ways, creating observable disturbances in the charged particle environment as it approaches the inner solar system. Instead, Measurements from deep space probes detect magnetic anomalies that appear and disappear without following established patterns for comet plasma interactions. The forbidden zones become particularly problematic when astronomers attempt to trace 3Y/Atlas's trajectory backward through time, seeking to understand its origins and the stellar encounters that shaped its billion-year journey to our solar system. Orbital mechanics allows precise reconstruction of past motion when all forces are well understood. But for this interstellar visitor, backward integration produces increasingly chaotic results as calculations extend into the past. Within a few million years, the mathematical uncertainty envelope expands to encompass virtually the entire galaxy, making definitive statements about the comet's origins impossible. Galactic dynamics introduces another layer of forbidden complexity. As 3I/Atlas traveled between star systems, it moved through the galaxy's gravitational potential well, experiencing tidal forces from the distribution of stellar masses, dark matter, and interstellar gas clouds. Current galactic models remain crude approximations that work well for understanding large-scale structure, but break down when applied to the precise trajectories of individual objects over cosmological timescales. The comet carries within its orbital parameters the accumulated effects of encounters with gravitational environments that Earth-based astronomy can only approximate. The mathematical crisis deepens when astronomers consider the possibility that 3Y/Atlas has been influenced by gravitational waves during its interstellar journey. These ripples in space-time, produced by accelerating masses throughout the universe, create tiny but potentially cumulative effects on objects traveling vast distances. Current gravitational wave detectors remain sensitive only to the strongest signals from black hole mergers and neutron-star collisions, leaving an entire spectrum of weaker gravitational radiation unmeasured and unmodeled. The comet's trajectory anomalies could represent the first indirect detection of this background gravitational wave environment. Quantum mechanical effects, typically negligible for macroscopic objects, may become relevant for understanding 3I/Atlas's motion through the quantum vacuum of interstellar space, the Casimir effect, which produces measurable forces between closely spaced parallel plates in laboratory conditions, could create subtle accelerations on comet-sized objects traveling through regions where virtual particle densities vary with local gravitational fields. These quantum corrections to classical motion remain entirely theoretical for astronomical applications, but 3I/Atlas's anomalous behavior suggests that such effects may be observable on cosmic scales. The comet's approach to the forbidden zone at 12 astronomical units, roughly the orbit of Saturn, triggers computational avalanches in the supercomputer clusters dedicated to solar system modeling. Integration algorithms that maintain stability for thousands of years when modeling planetary motion develop catastrophic numerical instabilities within months when applied to 3I/Atlas in this region. The mathematical breakdown appears to result from resonance effects with gravitational harmonics that remain poorly understood even for our familiar solar system environment. Chaos theory provides frameworks for understanding how small uncertainties can grow exponentially in complex dynamical systems. But even these sophisticated mathematical tools struggle with 3I/Atlas's trajectory through the forbidden zones. The comet's motion exhibits sensitive dependence on initial conditions that exceeds the chaotic behavior observed in asteroid populations near Jupiter's Trojan points, or in the complex dynamics of Saturn's ring system. Something about its interstellar origin has endowed 3I/Atlas with mathematical properties that push chaos theory itself toward its limits. Alternative theories of gravity, developed to explain cosmic acceleration and dark matter without invoking exotic substances, make specific predictions about how massive objects should behave in the weak gravitational fields that characterize the outer solar system. Modified Newtonian dynamics, MUOND, scalar tensor theories, and extra-dimensional models each suggest subtle deviations from Einstein's general relativity that could become detectable through precise measurements of object trajectories in these low-acceleration environments. 3I/Atlas's motion through the forbidden zones provides an unprecedented opportunity to test these theories. But the comet's behavior appears to match none of them completely. The mathematical rebellion spreads through international networks of astronomers as observatories around the world attempt to contribute to the orbital solution. Astrometric measurements from different telescopes, reduced using identical software packages and coordinate systems, produce position measurements that disagree by amounts far exceeding their stated uncertainties. The comet appears to occupy slightly different locations in space depending on which instruments observe it, as if its position contains some fundamental indeterminacy that cannot be reduced through improved measurement techniques. Statistical analysis reveals that 3I/Atlas's positional uncertainties exhibit non-Gaussian distributions that violate the assumptions underlying standard error propagation methods. Instead of the familiar bell curves that characterize measurement errors in typical astronomical observations, the comet's position residuals display heavy tails and asymmetries that suggest underlying physical processes operating beyond the reach of current theory. These anomalous error distributions force astronomers to develop new statistical methods for handling data that refuses to conform to established patterns. Machine learning algorithms, trained on decades of solar system orbital data, fail catastrophically when applied to 3I/Atlas trajectory prediction. Neural networks that successfully interpolate and extrapolate planetary motions produce wildly inconsistent results when confronted with this interstellar visitor's motion through the forbidden zones. The artificial intelligence systems appear to encounter the same mathematical barriers that challenge traditional physics-based modeling approaches, suggesting that the comet's anomalous behavior reflects fundamental gaps in our understanding rather than mere computational limitations. International space agencies quietly begin revising mission planning protocols as 3I/Atlas demonstrates that objects from interstellar space may not behave according to the gravitational rules that govern solar system dynamics. Spacecraft trajectory calculations, which rely on precise knowledge of gravitational fields throughout the solar system, must now account for the possibility that interstellar visitors carry with them unknown physics that could affect mission success. The comet's passage through forbidden zones forces engineers to expand their safety margins and develop contingency plans for encounters with gravitational environments that Earth-based testing cannot simulate. As winter deepens and 3I/Atlas continues its approach through regions where mathematics breaks down, astronomers find themselves in the uncomfortable position of acknowledging the limits of their predictive capabilities. The visitor from interstellar space moves through the forbidden zones with apparent indifference to the computational chaos it creates, carrying within its trajectory the quiet suggestion that the universe operates according to rules more subtle and complex than Earth's physics has yet discovered, in the deep cold of space where theory meets reality. A single comet rewrites the boundaries of human knowledge, one orbital calculation at a time, in the sterile silence of laboratory spectrographs, where light from 3I/Atlas spreads across detector arrays like whispered secrets from the void. Astronomers discover that ancient ice carries chemistry older than our world. The water molecules locked within the comet's nucleus tell stories of formation in molecular clouds that never knew our sun's warmth, their isotopic signatures bearing witness to stellar nucleosynthesis that occurred when the galaxy was younger and the local stellar neighborhood contained different populations of massive stars. The deuterium to hydrogen ratio in 3I/Atlas's sublimating ice deviates significantly from solar system norms, suggesting origins in regions of space where temperature and density conditions during the early universe's chemical evolution differed from those that characterized our own stellar nursery. These heavy water molecules, carrying extra neutrons forged in the primordial nucleosynthesis that followed cosmic inflation, reveal that the comet formed in environments where the universe's fundamental constants express themselves through different chemical pathways. Dr. Michael Torres adjusts the spectrograph's gratings as 3 I/Atlas's light resolves into absorption lines that challenge decades of experience in astronomical spectroscopy. The familiar signatures of water vapor, carbon monoxide, and simple hydrocarbons appear alongside molecular features that match no known terrestrial or meteoritic materials. These alien spectral lines correspond to chemical bonds that Earth's chemistry has never produced naturally, suggesting that interstellar space hosts molecular architectures impossible under terrestrial conditions. The comet's nitrogen isotope ratios paint pictures of stellar environments where massive stars underwent supernova explosions with different heavy element yields than those that enriched our solar nebula. The 15N/14N signature in sublimating ammonia and organic compounds indicates formation in molecular clouds that had been enriched by different generations of stellar nucleosynthesis. Carrying within frozen ices the chemical memories of galactic evolution that preceded our sun's birth by hundreds of millions of years. Xenon isotopes trapped in the comet's crystalline water ice provide particularly compelling evidence for alien origins. These noble gas atoms, captured during the comet's formation in interstellar space, exhibit isotopic patterns that differ systematically from all solar system materials. The xenon signatures point to nucleosynthesis in our process environments, the rapid neutron capture events that occur in neutron star mergers and core collapse supernovae, that operated with different neutron densities and timescales than those that contributed heavy elements to our solar system's formation. Organic compounds sublimating from 3 I/Atlas's nucleus carry molecular complexities that terrestrial biochemistry has never achieved. Polycyclic aromatic hydrocarbons with unusual substitution patterns suggest formation through chemical pathways that operate only in the extreme cold of interstellar space, where reaction rates slow to timescales measured in millions of years and molecular evolution follows different rules than those governing terrestrial organic chemistry. The comet's sulfur chemistry reveals particularly exotic signatures. Hydrogen sulfide and more complex sulfur-bearing compounds exhibit isotopic ratios that indicate processing through photochemical reactions driven by cosmic ray bombardment during the long journey between stellar systems. These chemical modifications, accumulated over eons of exposure to high-energy particles in interstellar space, create molecular fingerprints unlike anything preserved in solar system materials that have remained protected within our sun's magnetic influence. Amino acid precursors detected in the comet's outgassing plume carry chirality signatures, molecular handedness, that differ from the left-handed preference observed in terrestrial biology. These alien organic molecules suggest that the chemical processes leading toward biological complexity may follow different stereochemical rules in environments where cosmic ray bombardment and extreme cold create reaction conditions impossible to replicate in Earth-based laboratories. The water ice itself exhibits crystalline structures that form only under specific pressure and temperature conditions that existed in the dense molecular clouds where 3 I/Atlas originated. These exotic ice phases, more familiar to high-pressure physics researchers than to planetary scientists, indicate formation environments where gravitational compression from surrounding interstellar matter created pressures exceeding those found anywhere in our current solar system. Trace element abundances in the sublimating material reveal depletion patterns that reflect the chemical evolution of interstellar dust grains over cosmological timescales. Elements that condense onto grain surfaces in cold molecular clouds have been selectively removed from the gas phase, creating abundance ratios that differ systematically from solar values. These chemical signatures provide insights into dust-gas interactions that operated in the interstellar medium long before our solar system's formation. The comet's carbon isotope chemistry tells stories of processing through multiple stellar environments during its journey across the galaxy. The 13C/12C ratio in sublimating carbon monoxide and organic compounds indicates origins in regions where asymptotic giant branch stars had contributed different isotopic signatures to the local interstellar medium than those that characterized our solar nebula's formation environment. Metallic species detected in the comet's spectrum exhibit oxidation, states that suggest chemical processing in environments where oxygen fugacity differed dramatically from solar system conditions. Iron, magnesium, and silicon compounds display molecular configurations that form only under the extremely reducing conditions that characterize dense molecular cloud cores, where hydrogen dominates all chemistry and metals, exist in oxidation states rarely observed in terrestrial materials. The comet's phosphorus chemistry provides particularly intriguing insights into the potential for biological complexity in interstellar environments. Phosphine and more complex phosphorus-bearing organic molecules suggest chemical pathways that could lead toward the phospholipid membranes and nucleic acid backbones essential for life as we understand it. Yet these alien phosphorus compounds exhibit molecular architectures that differ subtly from their terrestrial counterparts, hinting at alternative biochemistries that might evolve under different environmental conditions. Noble gas abundances trapped within 3I/Atlas's ices reveal the signature of cosmic ray spallation reactions that operated during the comet's journey through regions of space where galactic cosmic ray intensities exceeded those experienced within our solar system's protective heliosphere. Helium and neon isotopes produced by high-energy particle bombardment of heavier nuclei provide chronometers for the duration of interstellar exposure, suggesting travel times measured in tens of millions of years between stellar systems. Molecular hydrogen ortho-to-para ratios in the comet's sublimating gases reflect the extremely low temperatures that characterized its formation environment. These quantum mechanical spin state distributions, which equilibrate slowly at interstellar temperatures, preserve information about the thermal history of the molecular cloud where 3I/Atlas originated, providing insights into the physical conditions that prevailed in star-forming regions when our galaxy was younger. The discovery of pre-solar grains embedded within the comet's nucleus reveals that 3Y/Atlas incorporated solid materials that formed around other stars before being ejected into interstellar space through stellar winds and supernova explosions. These microscopic crystals of silicon carbide, graphite, and exotic oxides carry within their crystal lattices the isotopic signatures of specific stellar nucleosynthesis processes, providing direct samples of materials formed in the interiors of stars that died billions of years before our sun was born. Chemical kinetics modeling suggests that many of 3Y/Atlas's exotic molecular species could only have formed through reaction pathways that operate on timescales far longer than the age of our solar system. The comet's chemistry represents a kind of interstellar fermentation, where extremely slow reaction rates in cold molecular clouds allow complex organic synthesis to proceed through pathways impossible under terrestrial conditions, creating molecular libraries that sample the full range of carbon chemistry possible in the universe, as 3I/Atlas continues its approach through the outer solar system. Each spectroscopic observation reveals new layers of chemical complexity that challenge our understanding of how matter behaves in the cold darkness between stars. The visitor from interstellar space carries within its ancient ices a chemistry textbook written in languages that Earth's molecular evolution never learned to speak, offering glimpses into the vast chemical diversity that exists in the galaxy beyond our sun's familiar influence, beyond Neptune's distant orbit, where solar gravity weakens to whispers and interstellar space begins its patient encroachment upon our sun's domain. 3I/Atlas crosses the theoretical boundary that marks the edge of human understanding, The Oort cloud extends its invisible tendrils into regions where comet nuclei sleep in orbits so vast that they barely acknowledge our star's existence. Yet even this remote frontier represents familiar territory compared to the true interstellar void from which our visitor emerges. The heliopause, that dynamic boundary where solar wind meets interstellar medium, shifts and breathes with the 11-year solar cycle, sometimes expanding beyond 120 astronomical units, sometimes contracting to barely 100. Here, charged particles from our Sun finally exhaust their energy against the neutral hydrogen that fills the space between stars, creating a turbulent mixing zone where two fundamentally different environments struggle for dominance. 3 I/Atlas has crossed this boundary from the outside, carrying within its trajectory the gravitational memories of spaces where our Sun's influence never reached. Theoretical models of the outer solar system rely heavily on observations of Voyager 1 and Voyager 2, those intrepid spacecraft that first crossed into interstellar space and began transmitting data from regions no human instrument had ever explored. Their measurements revealed that the transition from solar-dominated to interstellar-dominated space occurs gradually across several astronomical units, with magnetic field orientations, particle densities, and plasma temperatures changing in complex ways that challenge simplified boundary models. For 3 I/Atlas, this transition zone represents merely another region of space through which it has moved with the same patient persistence that has characterized its billion-year journey between stellar systems. The comet's trajectory shows no evidence of perturbation by the heliopause crossing, suggesting that objects of interstellar origin interact with this boundary layer differently than the solar wind and magnetic fields that define it for spacecraft of terrestrial origin. The Kuiper Belt, that distant disk of icy bodies that includes Pluto and thousands of smaller objects, marks the beginning of our solar system's extended architecture. These primordial remnants preserve chemical and physical signatures from the epoch of planetary formation, their compositions and orbits providing insights into the conditions that prevailed when our Sun first ignited nuclear fusion and began sculpting the matter in its vicinity. Yet even these ancient objects remain fundamentally solar in character, their existence defined by gravitational relationships with our star that have persisted for billions of years. 3 I/Atlas moves through this familiar territory with the detached air of a traveler passing through foreign countryside. Its hyperbolic trajectory acknowledges the gravitational influence of Neptune and the other outer planets, while maintaining the fundamental independence that characterizes objects whose origins lie beyond our Sun's gravitational reach. The comet's orbital elements speak of spaces where different stars provided the dominant gravitational influence, where the physical laws remain identical but express themselves through entirely different boundary conditions. Gravitational modeling of the outer solar system becomes increasingly approximate as distances from the Sun increase beyond the orbits of the giant planets. The inverse square law that governs gravitational attraction continues to operate with mathematical precision, but the practical effects of solar gravity become comparable to perturbations from passing stars, galactic tidal forces, and the distributed mass of the Oort cloud itself. In these regions, the clean simplicity of two-body orbital mechanics gives way to the complex choreography of the galaxy-scale n-body problem, the local interstellar cloud, a low-density region of partially ionized gas through which our entire solar system currently moves, creates environmental conditions that existed nowhere during the era of planetary formation. This tenuous medium, with particle densities measured in atoms per cubic centimeter, nonetheless exerts subtle influences on objects traveling at interstellar velocities. 3 I/Atlas has spent eons moving through similar environments, its surface chemistry and internal structure shaped by interactions with interstellar matter that our solar system has experienced only recently in cosmic terms. Magnetic field measurements from deep space probes reveal that the interstellar medium carries organized magnetic structures that extend across parsecs of space. Remnants of stellar winds and supernova shockwaves that have shaped the local galactic environment for millions of years. These fields, though incredibly weak by terrestrial standards, can influence the trajectories of charged particles and may create subtle electromagnetic effects on conducting materials within comet nuclei during their long journeys between stellar systems. The cosmic ray environment in interstellar space differs dramatically from that experienced within our solar system's protective magnetic bubble. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent astrophysical processes, penetrate interstellar matter with intensities that exceed those measured within the heliosphere. 3I/Atlas has been bathed in this radiation environment for eons, its surface layers modified by nuclear reactions that create isotopic signatures impossible to produce under solar system conditions. Gravitational waves from distant astrophysical sources propagate through interstellar space with amplitudes that, while tiny, could accumulate measurable effects over the millions of years required for objects to travel between stellar systems. These ripples in space-time, produced by accelerating masses throughout the universe, represent a background gravitational environment that remains largely unmeasured and unmodeled. The subtle trajectory anomalies exhibited by 3I/Atlas could provide the first indirect evidence of how this gravitational wave background influences the motion of massive objects over cosmological timescales. The transition from bound to unbound orbits marks a fundamental change in how objects relate to gravitational systems. Solar system bodies move in elliptical paths that eventually return them to their starting positions, their futures as predictable as their pasts within the framework of celestial mechanics. Interstellar objects like 3I/Atlas follow hyperbolic trajectories that carry them ever farther from their points of closest approach, their futures extending into regions of space that our telescopes cannot observe and our theories can barely imagine. Dark matter, that mysterious substance that comprises most of the universe's gravitational mass, may create detectable effects on objects traveling interstellar distances even though its influence remains unobservable for solar system dynamics. Current models suggest that dark matter particles interact only through gravity, but their cumulative effects over millions of years of interstellar travel could produce the kinds of subtle trajectory modifications that 3I/Atlas appears to exhibit. The comet's motion through regions where dark matter densities vary could provide unprecedented insights into the properties of this elusive cosmic component. Stellar encounters during 3I/Atlas's journey between stellar systems have left gravitational fingerprints on its current trajectory that carry information about the local galactic environment extending back millions of years. Each close approach to a star or brown dwarf has modified the comet's velocity vector in ways that preserve information about stellar masses, distances, and encounter geometries. Decoding these gravitational memories requires understanding the local stellar kinematics over timescales that exceed direct observational records. The galactic tide, produced by the differential gravitational effect of the Milky Way's mass distribution, creates forces that become significant only for objects traveling the vast distances characteristic of interstellar space. This tidal influence, negligible for solar system dynamics, may have shaped 3I/Atlas's trajectory in ways that provide insights into the galaxy's dark matter distribution and the three-dimensional structure of stellar populations in our local galactic neighborhood. As 3I/Atlas moves deeper into our solar system's gravitational well, it carries with it the accumulated influences of environments that exist beyond the comfortable boundaries of Earth-based astronomy. The visitor from interstellar space has crossed theoretical limits that mark not physical barriers, but the edges of human knowledge, bringing into our familiar cosmic neighborhood the gentle suggestion that the universe operates according to rules more subtle and far-reaching than our models can yet comprehend. In the gravitational theater, where 3I/Atlas performs its slow ballet with our sun and planets, subtle anomalies accumulate like whispered accusations against the fundamental laws that have governed celestial mechanics since Newton first glimpsed the mathematical harmony underlying planetary motion. The comet's trajectory exhibits deviations that exceed the predictive power of standard gravitational theory, as if additional forces operate in the cold darkness between worlds. Forces that remain invisible to our instruments but manifest their presence through the patient rebellion of ice and rock against theoretical expectations. The most perplexing anomalies emerge in the comet's non-gravitational accelerations, those tiny changes in velocity that solar radiation pressure and outgassing should explain completely. For typical comets born in our solar system's Oort cloud, these forces follow well-understood patterns. Solar heating creates preferential outgassing on the sun-facing hemisphere, producing rocket-like thrust that gradually modifies orbital elements in predictable ways. The magnitude and direction of these accelerations correlate directly with heliocentric distance, surface composition, and rotation period through relationships that have been verified across hundreds of cometary observations. 3I/Atlas refuses to conform to these established patterns. Its non-gravitational accelerations exhibit periodicities that correlate weakly with solar heating cycles and show directional preferences that suggest forces operating independently of the comet's orientation relative to the Sun. These anomalous accelerations persist even when the comet remains too distant for significant solar heating to occur, implying the presence of energy sources or force mechanisms that standard cometary physics cannot explain. Dr. Yuki Tanaka studies trajectory integration results that challenge 40 years of experience in orbital dynamics. Her numerical models, refined through successful application to dozens of comet encounters, produce prediction errors that grow systematically as 3I/Atlas approaches the inner solar system. The comet consistently appears slightly ahead of or behind its predicted position. The discrepancies following patterns that suggest underlying periodicity but resist correlation with any known physical process. The gravitational influence of Jupiter, that giant planet whose massive presence shapes the architecture of our entire solar system, should dominate perturbation calculations for objects passing through the outer planetary regions. Jupiter's gravity wells, mapped with extraordinary precision through spacecraft missions and centuries of observation, create predictable changes in orbital elements that allow astronomers to trace comet trajectories forward and backward through time with remarkable accuracy. Yet 3I/Atlas appears to experience Jovian perturbations that deviate from theoretical predictions by amounts that exceed all reasonable estimates of observational uncertainty. Saturn's gravitational signature presents similar mysteries. The ringed planet's complex system of moons and gravitational resonances creates a rich environment of orbital perturbations that spacecraft navigators have learned to exploit for trajectory modifications. These same gravitational complexities should affect 3I/Atlas's motion in calculable ways, yet the comet's response to Saturn's influence suggests additional mass concentrations or gravitational effects that current models cannot account for. The possibility of undiscovered massive objects in the outer solar system has intrigued astronomers for decades. Planet 9, a hypothetical super-Earth orbiting beyond Neptune's influence, could create gravitational perturbations that affect the trajectories of distant objects, including interstellar visitors. Yet the specific anomalies exhibited by 3I/Atlas do not match predictions for Planet 9's gravitational signature, suggesting either that this proposed planet does not exist or that the comet's trajectory anomalies have different origins entirely. Modified theories of gravity, developed to explain cosmic acceleration and galaxy rotation curves without invoking dark matter or dark energy, make specific predictions about how gravitational forces should deviate from Newton's inverse square law in the weak field regime that characterizes the outer solar system. These theories, including modified Newtonian dynamics, MONDD, scalar tensor gravity, and extra-dimensional models, suggest that gravitational acceleration should exhibit anomalies when the local gravitational field strength falls below certain critical thresholds. The gravitational field strength at 3y/Atlas's current position barely exceeds the critical acceleration scale predicted by Hammond theory, making it an ideal test case for these alternative gravitational theories. Yet the comet's motion exhibits anomalies that match none of these theoretical frameworks completely, suggesting either that modified gravity theories require further development or that additional physical mechanisms contribute to the observed trajectory deviations. Electromagnetic effects, though typically negligible for celestial mechanics calculations, could become relevant for objects carrying significant electric charge through regions where magnetic fields and plasma densities vary. The solar wind creates an electromagnetic environment that extends throughout the solar system, its structure modified by planetary magnetospheres and the complex dynamics of charged particle interactions. An electrically charged comet nucleus could experience Lorentz forces that produce measurable trajectory modifications, especially in regions where magnetic field gradients are steep. The possibility that 3I/Atlas carries significant electric charge gained during its journey through the interstellar medium remains speculative but intriguing. Cosmic ray bombardment and photoelectric effects from stellar radiation could gradually build up charge imbalances on interstellar objects, creating electric potentials that persist for geological timescales in the high vacuum environment of space. Such charged objects would experience forces proportional to their velocity through magnetic fields, potentially explaining the anomalous accelerations that appear independent of solar heating effects. Gravitational lensing effects from dark matter concentrations represent another potential explanation for the observed trajectory anomalies. While dark matter's gravitational influence remains undetectable for solar system dynamics, its cumulative effects over the long timescales characteristic of interstellar travel could produce subtle modifications to object trajectories that become apparent only for visitors from beyond the heliosphere. The distribution of dark matter in our local galactic environment remains poorly constrained, leaving open the possibility that 3E/Atlas has been influenced by gravitational fields that Earth-based astronomy has never directly observed. The comet's interaction with the galactic magnetic field during its interstellar journey could have induced internal magnetic moments that now interact with the solar system's electromagnetic environment in unexpected ways. Ferromagnetic materials within the comet nucleus, magnetized by exposure to interstellar magnetic fields over millions of years, could create magnetic dipoles that experience torques and forces when moving through the structured magnetic fields associated with solar wind and planetary magnetospheres. Tidal effects from the galaxy's differential gravitational field, though minute for solar system objects, accumulate significance for bodies that have traveled interstellar distances. The Milky Way's gravitational gradient creates tidal forces that vary with galactic position, potentially leaving signatures on the internal structure and rotation state of objects that have journeyed across significant fractions of our galactic disk. These tidal memories could manifest as anomalous mechanical properties that affect how the comet responds to external forces during its solar system passage. Vacuum fluctuations and quantum field effects, typically irrelevant for macroscopic objects, might become detectable for bodies that have spent eons in the extreme vacuum of interstellar space. The Casimir effect and related quantum mechanical phenomena could create tiny but persistent forces that accumulate measurable effects over the vast timescales and distances characteristic of interstellar travel. While these quantum corrections to classical mechanics remain entirely theoretical for astronomical applications, 3I/Atlas's anomalous behavior suggests that the boundary between quantum and classical physics may be more subtle than current theories assume. As the comet continues its approach through regions where gravitational anomalies challenge theoretical understanding, astronomers find themselves confronting the possibility that our models of space, time, and matter require fundamental revision. The visitor from interstellar space moves through our solar system with the quiet persistence of a natural experiment operating on scales that Earth-based physics has never directly tested, suggesting that the universe operates according to principles more complex and beautiful than human knowledge has yet discovered. Between the scattered islands of stellar systems, where matter exists in densities so low that each cubic meter of space contains fewer atoms than a single breath of Earth's atmosphere. 3I/Atlas has journeyed through environments that stretch the boundaries of what we consider empty space. The interstellar medium, that tenuous sea of gas and dust that fills the galaxy between stars, creates conditions unlike anything found within our solar system's protective bubble, its subtle influences accumulating over millions of years to shape the trajectory and composition of objects brave enough to cross such vast distances. The local interstellar cloud, through which our entire solar system currently moves at 26 kilometers per second, represents just one small bubble in the complex foam of heated and cooled gas that characterizes our galactic neighborhood. This partially ionized medium, with temperatures reaching 10,000 Kelvin, despite particle densities measured in fractions of atoms per cubic centimeter, carries within its structure the layered history of stellar winds, supernovae shockwaves, and the slow cooling of material heated by ancient stellar explosions. 3I/Atlas has spent eons navigating through similar environments, its surface bombarded by cosmic rays at intensities that exceed those experienced within our sun's magnetic shelter by factors of hundreds or thousands. These high-energy particles, accelerated to relativistic velocities by supernova shock fronts and other violent astrophysical processes, penetrate deeply into solid matter, creating isotopic modifications and chemical changes that serve as chronometers for the duration of interstellar exposure. Dr. Rebecca Stone analyzes spectroscopic data that reveals the comet's surface chemistry, bears signatures of processing through multiple interstellar environments during its journey to our solar system. The isotopic ratios of rare elements produced by cosmic ray spallation reactions suggest exposure times measured in tens of millions of years, while the presence of exotic molecular species indicates chemical processing under conditions that exist only in the cold. Low-pressure environments characteristic of molecular clouds, dense molecular clouds, where star formation actively redistributes matter and energy, represent the most complex environments through which interstellar objects must navigate during their journeys between stellar systems. These regions, with particle densities that can exceed 1 million atoms per cubic centimeter, create gravitational perturbations and chemical processing conditions that leave permanent imprints on passing objects. The molecular hydrogen that dominates these clouds exists primarily in its lowest rotational and vibrational states, creating a medium that behaves unlike any gas found in terrestrial or solar system environments. The magnetic field structure within molecular clouds follows complex patterns that reflect the interplay between turbulent gas motions, stellar winds from embedded young stars, and the magnetic pressure of charged particles accelerated by stellar formation processes. These fields, though incredibly weak by terrestrial standards, extend across parsecs of space and can influence the trajectories of charged particles and weakly conducting materials over the vast timescales characteristic of interstellar travel. 3I/Atlas's current trajectory suggests encounters with at least 3 distinct molecular cloud complexes during its journey to our solar system, each interaction leaving subtle chemical and physical signatures that provide insights into environments that Earth-based astronomy can observe only from vast distances. The comet's surface composition reflects processing through regions where carbon monoxide freezes onto dust-grained surfaces, where complex organic molecules form through surface chemistry reactions that operate at temperatures barely above absolute zero. Stellar winds from massive stars create bubbles of heated, low-density gas that can extend for hundreds of light-years around their sources. These environments, characterized by temperatures exceeding 1 million Kelvin and particle velocities that approach significant fractions of the speed of light, represent some of the most extreme conditions in the interstellar medium. Objects passing through such regions experience intense radiation fields and particle bombardment that can modify their surface properties and internal structure in ways that persist long after they escape into cooler environments. The comet's encounter with our solar system's heliopause marks its first interaction with a stellar wind environment in millions of years. The boundary where solar wind meets interstellar medium creates a complex zone of magnetic field reconnection, particle acceleration, and plasma instabilities that spacecraft measurements have only begun to characterize. 3. I/Atlas crosses this boundary from the outside with velocity vectors that carry information about the interstellar medium's bulk motion relative to our Sun's path through the galaxy. Supernova shockwaves, propagating through the interstellar medium at velocities measured in thousands of kilometers per second, create some of the most dramatic environmental changes that interstellar objects can experience during their journeys between stellar systems. These expanding shells of heated gas and accelerated particles can overtake and engulf slower-moving objects, subjecting them to intense radiation fields and particle bombardment that can strip away surface layers and modify chemical compositions in fundamental ways. The comet's chemical signatures suggest at least one close encounter with such a shock front, evidenced by isotopic ratios that indicate processing through high-temperature, high-pressure environments unlike anything found in quiescent interstellar space. The rare Earth elements embedded in its crystalline structure carry the fingerprints of nucleosynthesis processes that operate only in the extreme conditions found behind supernova shockwaves, suggesting that 3I/Atlas has sampled directly the stellar matter ejected during massive star explosions. H2 regions, zones of ionized hydrogen surrounding hot, massive stars, create environments where ultraviolet radiation with photon energies exceeding 13 electron volts can break chemical bonds and ionize atoms across volumes measured in hundreds of cubic light years. These regions represent natural laboratories for studying atomic and molecular physics under conditions impossible to reproduce in Earth-based facilities. Their complex chemistry, driven by radiation fields that exceed solar ultraviolet intensities by orders of magnitude. The molecular inventory detected in 3I/Atlas's outgassing suggests processing through such environments, evidenced by the presence of unusual organic compounds that form only under intense ultraviolet irradiation, combined with the extremely low densities characteristic of ionized gas. These chemical signatures provide insights into photochemical processes that operate in regions where radiation pressure dominates over thermal pressure, creating reaction pathways that differ fundamentally from those accessible under terrestrial conditions. Gravitational focusing effects from massive stellar objects can concentrate the trajectories of interstellar matter into streams and filaments that persist across galactic scales. 3I/Atlas may have followed such a gravitational channel during part of its journey, its path shaped by the collective gravitational influence of stellar clusters or massive molecular cloud complexes that created preferred routes for interstellar material transport. These gravitational highways, invisible to direct observation, leave signatures in the arrival directions and velocity distributions of interstellar objects that enter solar systems throughout the galaxy. The cosmic web structure of dark matter and ordinary matter on galactic scales creates large-scale gravitational gradients that influence the motion of objects traveling interstellar distances, filaments of enhanced dark matter density, connecting galactic mass concentrations across millions of light-years, may channel the flow of interstellar objects along preferred directions that reflect the underlying cosmic structure. 3I/Atlas's arrival trajectory could provide insights into this cosmic architecture, its path carrying information about dark matter distributions that operate on scales far larger than individual stellar systems, magnetic field reconnection events in the interstellar medium triggered by the collision of gas streams with different magnetic orientations, create localized acceleration regions where charged particles gain energy, and neutral atoms experience forces through collision coupling with the accelerated ions. These reconnection sites, though rare, can dramatically modify the trajectories of passing objects while simultaneously altering their surface chemistry through exposure to enhanced particle fluxes and modified magnetic field configurations. As 3I/Atlas continues its passage through the solar system, carrying within its structure the accumulated influences of environments that span the range of physical conditions found in our galaxy's interstellar medium. Astronomers recognize that this visitor from the void provides an unprecedented opportunity to study processes that operate across scales of space and time that dwarf human experience. The comet moves through our familiar solar system environment with the detached patience of an object that has learned to navigate conditions where matter and energy express themselves through mechanisms that Earth-based physics is only beginning to understand. At 4 astronomical units from the Sun, where asteroid belt debris marks the boundary between rocky inner planets and gas giant outer worlds. 3I/Atlas begins its transformation from dormant interstellar wanderer to active comet. Solar radiation, strengthening with each passing day as the inverse square law concentrates stellar energy onto the comet's ancient surface, initiates sublimation processes that will release gases locked in crystalline ice structures for millions of years since the visitor's formation in cold molecular clouds beyond our stellar neighborhood. The sublimation threshold for water ice occurs when solar heating raises surface temperatures above approximately 150 Kelvin, still colder than Antarctica's winter, but sufficient to drive the phase transition that bypasses liquid water entirely in the vacuum of space. For 3I/Atlas, this transformation begins gradually, starting with the most volatile compounds: carbon monoxide, carbon dioxide, nitrogen, that require less energy to escape their frozen crystalline matrices. Dr. Amanda Chen monitors thermal infrared observations as the comet's surface begins radiating excess heat, the first sign that solar energy absorption exceeds thermal emission into the cosmic microwave background. Her instruments detect temperature variations across the nucleus that suggest heterogeneous composition, with some regions heating more rapidly than others as different materials respond to solar radiation according to their thermal properties and albedo characteristics. The outgassing process operates through mechanisms that remain poorly understood even for comets originating within our solar system, as volatile ices sublimate beneath the surface. Expanding gases must escape through tortuous pathways within the porous cometary matrix, creating internal pressure gradients that can fracture rock and reorganize the nucleus structure. For 3I/Atlas, this process releases compounds that formed under interstellar conditions, creating chemical signatures that challenge standard models of cometary activity. Jets of sublimating material begin appearing on the comet's day side, visible as faint streaks against the stellar background when observed through powerful ground-based telescopes. These jets follow trajectories determined by the nucleus's rotation and local topography, creating patterns that reveal information about the comet's internal structure and composition distribution, unlike typical solar system comets. 3I/Atlas's jets exhibit directional preferences that correlate weakly with solar illumination patterns, suggesting subsurface volatile distributions shaped by interstellar processing rather than solar heating cycles. The developing coma, that tenuous atmosphere of gas and dust that surrounds active comets, begins expanding outward at velocities determined by the temperature and molecular weight of sublimating species. Water vapor molecules escape at speeds approaching 1 kilometer per second, while lighter compounds like carbon monoxide achieve escape velocities that exceed 2 kilometers per second. This differential expansion creates a complex chemical environment where different molecular species occupy distinct spatial regions within the growing coma. Photodissociation processes begin operating as solar ultraviolet radiation breaks apart complex molecules released from the comet's interior. Water molecules split into hydrogen and hydroxyl radicals. Carbon dioxide decomposes into carbon monoxide and atomic oxygen, and organic compounds fragment into smaller molecular species that create the rich emission line spectrum characteristic of active comets. For 3I/Atlas. These photochemical processes act upon molecular precursors unlike any found in solar system materials, creating spectral signatures that require new databases of molecular transition probabilities. The comet's albedo, its ability to reflect rather than absorb solar radiation, proves crucial for determining heating rates and sublimation patterns. Most comet nuclei exhibit albedos between 3 and 7%, making them among the darkest objects in the solar system. These low reflectivities result from organic compounds that polymerize under cosmic ray bombardment, creating dark surface crusts that efficiently absorb solar radiation. 3I/Atlas exhibits albedo variations that suggest surface composition heterogeneities related to its unique formation and processing history in interstellar space. Dust particles liberated by sublimating gases begin forming the visible dust tail that will eventually extend millions of kilometers anti-sunward, driven by solar radiation pressure acting on microscopic grains. These dust particles, ranging in size from nanometers to millimeters, carry within their crystalline structures the mineral record of the comet's formation environment. For an interstellar visitor, dust composition may include pre-solar grains, microscopic crystals that formed around other stars and survived incorporation into the comet during its assembly in molecular cloud environments. The development of the plasma tail represents a more complex process, involving ionization of neutral gas molecules by solar ultraviolet radiation and charge exchange with solar wind particles. The resulting ions, primarily from water vapor and carbon monoxide, become trapped in the solar magnetic field and are swept anti-sunward at velocities approaching solar wind speed. This plasma tail, though nearly invisible to optical telescopes, carries detailed information about the comet's gas production rates and composition. Sublimation-driven changes in the comet's rotation state create additional complications for orbital mechanics calculations, as jets of escaping gas create torques around the nucleus center of mass. The comet's rotation period and spin axis orientation evolve in ways that depend on the spatial distribution of active regions and volatile deposits. These non-gravitational torques can produce complex tumbling motions that affect how solar heating patterns evolve over time, creating feedback loops between thermal processes and rotational dynamics. The pristine nature of interstellar ice begins revealing itself through isotopic measurements of sublimating gases. Heavy water molecules containing deuterium, rare earth isotopes incorporated during pre-solar grain formation, and noble gas signatures trapped during molecular cloud processing create chemical fingerprints that distinguish 3I/Atlas from any solar system object. These measurements require the most sensitive spectrographic techniques available to astronomical observation, pushing the limits of what current instrumentation can detect and analyze. Surface erosion processes begin modifying the comet's nucleus structure as sublimation preferentially removes volatile rich materials while leaving behind refractory dust and organic residues. This differential mass loss creates topographic features, cliffs, valleys, and plateau regions that develop over time scales measured in orbital periods for typical comets, but represent the first such erosion that 3I/Atlas has experienced since its formation in interstellar space millions of years ago. The comet's approach toward perihelion triggers cascading changes in its thermal environment as solar flux increases according to the inverse square of heliocentric distance. Surface temperatures that began near 150 Kelvin will eventually exceed 300 Kelvin at closest solar approach, driving sublimation rates that increase exponentially with temperature according to the Clausius-Clapeyron relationship governing phase transitions in vacuum conditions. Crystalline structure transitions within the comet's water ice create additional complexity as amorphous ice, formed under the extremely cold conditions of interstellar space, undergoes irreversible transformation to crystalline phases when heated above approximately 130 Kelvin. This transition releases latent heat that can drive explosive outgassing events, creating sudden changes in activity levels that correlate with internal thermal wave propagation rather than external solar heating patterns. The exotic molecular species detected in 3I/Atlas's early outgassing suggest the presence of clathrate hydrates, cage-like water ice structures that trap guest molecules within their crystalline frameworks. These inclusion compounds can store volatile species at temperatures and pressures where they would normally remain gaseous, creating reservoirs of trapped gases that release suddenly when the hydrate structure destabilizes under solar heating. For an interstellar comet, these clathrates may contain molecular species unknown in solar system materials. Thermal modeling of the comet's interior reveals heat conduction timescales that exceed the duration of its solar system passage, meaning that temperatures at depths greater than a few meters remain largely unaffected by solar heating. This thermal inertia preserves pristine interstellar ice in subsurface regions, while surface layers undergo dramatic chemical and physical transformations. The resulting compositional gradients create complex outgassing patterns as different volatile species sublimate at different depth and temperatures. Infrared spectroscopy begins detecting silicate mineral features as dust particles in the expanding coma scatter and emit thermal radiation. These silicate signatures, characteristic of rocky materials that condense from high-temperature gas phases, provide insights into the conditions under which solid grains formed in the molecular cloud environment where 3I/Atlas originated. The mineral assemblages may differ systematically from those found in solar system materials, reflecting different pressure, temperature, and chemical conditions during dust grain condensation. The comet's magnetic properties begin manifesting as interactions with the solar wind's embedded magnetic field create detectable perturbations in the local plasma environment. Ferromagnetic minerals within the nucleus, magnetized during the comet's journey through interstellar magnetic fields, may create localized magnetic anomalies that affect how solar wind particles interact with the expanding coma. These magnetic signatures provide insights into the magnetic field environments that 3I/Atlas encountered during its interstellar journey. Solar wind charge exchange processes begin operating as solar wind protons encounter neutral atoms in the expanding coma, creating X-ray emission through radiative decay of highly excited charge exchange products. This X-ray emission, detectable by space-based telescopes, provides remote sensing capabilities for measuring the composition and density distribution of neutral gases around the comet nucleus. The charge exchange cross-sections for exotic molecular species found in interstellar materials may differ from those measured for typical solar system volatiles. As 3I/Atlas transforms from dormant interstellar wanderer to active comet, each aspect of this process reveals new information about the physical and chemical conditions that characterize environments beyond our solar system's boundaries. The sublimation of ancient ice, preserved in pristine condition for millions of years in the cold darkness between stars, offers unprecedented insights into the materials and processes that operate in regions of space where Earth-based astronomy can observe only the average signatures of vast, distant molecular clouds. The comet's awakening represents a natural experiment operating on scales of space, time, and temperature that dwarf any laboratory investigation possible within our terrestrial environment. As exotic ices sublimate into space, carrying with them the chemical memories of alien stellar neighborhoods and interstellar processing environments. 3I/Atlas begins writing across our solar system a story composed in molecular languages that Earth's chemistry never learned to speak. In the spectroscopic laboratories, where starlight surrenders its secrets to diffraction gratings and detector arrays, the emission spectrum of 3I/Atlas reveals absorption features that exist in no terrestrial database. These spectral lines, precise wavelength signatures of molecular transitions, correspond to energy level differences in chemical species that Earth's evolutionary chemistry never produced naturally, suggesting that the universe's molecular inventory extends far beyond what our planet's 4 billion years of chemical experimentation has discovered. The swan bands of diatomic carbon, normally prominent in comet spectra, appear alongside absorption features that require entirely new quantum mechanical calculations to interpret. Dr. Kenji Nakamura adjusts his spectrograph's wavelength calibration repeatedly, convinced initially that instrumental artifacts must explain the anomalous lines appearing between familiar molecular signatures. The wavelength positions remain constant across multiple observing sessions, their intensities varying with the comet's activity level in ways that confirm their origin in genuine molecular transitions rather than systematic measurement errors. Forbidden transitions, quantum mechanical processes that occur with extremely low probability under normal conditions, begin appearing in the comet's spectrum as the low-density environment of the expanding coma allows metastable atomic and molecular states to radiatively decay without collisional quenching. These forbidden lines, invisible in terrestrial atmospheric conditions where collision rates exceed radiative decay rates, provide insights into atomic and molecular physics operating under conditions impossible to reproduce in Earth-based laboratories. The hyperfine structure of hydrogen emission lines reveals isotopic ratios that differ systematically from solar system values, confirming that 3I/Atlas's water ice formed in environments where stellar nucleosynthesis had produced different heavy isotope abundances than those characterizing our local galactic neighborhood during the epoch of solar system formation. The deuterium to hydrogen ratio exceeds solar values by factors approaching 10, suggesting formation in regions where cosmic ray spallation or primordial nucleosynthesis had enhanced heavy isotope production through mechanisms that operated differently in the early galaxy. Molecular rotational temperatures, derived from the relative intensities of different rotational transitions within vibrational bands, indicate that sublimating gases achieve thermal equilibrium at temperatures significantly different from what standard sublimation models predict. These anomalous rotational temperatures suggest either that the comet's subsurface thermal environment differs from theoretical expectations, or that the molecular species themselves possess rotational energy distributions that reflect their formation under non-equilibrium conditions in interstellar space. The methane emission bands, typically weak features in comet spectra, exhibit enhancement patterns that suggest formation through catalytic processes operating on dust-grain surfaces under interstellar conditions. Grain surface chemistry, where hydrogen atoms adsorbed onto silicate or carbonaceous particles undergo reactions at temperatures approaching absolute zero, can produce complex organic molecules through pathways impossible under gas phase conditions. These surface-mediated reactions may have operated for millions of years during 3I/Atlas's journey through dense molecular clouds, building up reservoirs of organic compounds unlike any found in solar system materials. polycyclic aromatic hydrocarbon features, detected through their characteristic infrared emission bands, suggest the presence of complex carbon ring structures that may have formed through interstellar chemistry processes or survived incorporation from circumstellar environments around carbon-rich stars. These molecules, proposed as carriers of diffuse interstellar bands observed in stellar spectra, represent some of the most complex chemical structures found in space and provide insights into organic chemistry pathways that operate under conditions of extreme dilution and low temperature. Silicon monoxide emission, rarely detected in comet spectra, appears with intensities that suggest unusual silicon-bearing mineral compositions within the comet's dust component. This silicon chemistry may reflect condensation processes that operated in stellar winds from silicon-rich stars, creating mineral assemblages that differ from the magnesium-iron silicates that dominate solar system rocky materials. The silicon isotope ratios embedded in these emission features could provide insights into nucleosynthesis processes operating in stellar environments different from those that contributed heavy elements to our solar nebula. Rare earth element emission lines begin appearing as solar heating liberates trace metals incorporated into the comet's structure during its formation. These elements, produced primarily through slow neutron capture processes in asymptotic giant branch stars, carry isotopic signatures that reflect the stellar chemical evolution of whatever galactic region contributed matter to the molecular cloud where 3I/Atlas formed. The relative abundances of europium, gadolinium, and other rare earth elements may differ systematically from solar system ratios, providing insights into galactic chemical evolution operating on timescales exceeding the age of our solar system. The 21-centimeter hydrogen line, detectable only through radio telescopes, reveals the spin temperature and density distribution of neutral hydrogen atoms within the expanding coma. This hyperfine transition, forbidden under terrestrial conditions but prominent in the low-density environments of interstellar space, provides direct measurements of hydrogen atom populations and their velocity distributions as they escape from the comet nucleus. The line profile shapes carry information about turbulence and bulk motion within the coma that complements optical spectroscopic observations. Zeeman splitting of spectral lines in the comet's magnetic environment begins revealing the strength and structure of magnetic fields embedded within the expanding gas cloud. Solar wind interactions with the coma create complex magnetic field configurations that split degenerate atomic energy levels, creating multiple spectral components whose separation directly measures local magnetic field strength. These Zeeman effect measurements provide insights into how interstellar magnetic fields, frozen into the comet's conducting materials during its formation, interact with solar system electromagnetic environments. Molecular mazes, coherent amplification of specific molecular transitions, may begin operating within the comet's coma as population inversions develop in certain rotational or vibrational energy levels. These natural laser systems, common in circumstellar environments around evolved stars, could create intense emission at specific frequencies that provide highly sensitive probes of physical conditions within the expanding gas cloud. The threshold conditions for MESA operation depend critically on density, temperature, and radiation field strength, making their detection valuable for understanding coma dynamics. Isotopic ratios in carbon monoxide emission reveal processing through multiple stellar environments during the comet's interstellar journey. The 13C/12C ratio differs from solar values in ways that suggest incorporation of carbon that had been cycled through stellar interiors with different masses and metallicities than those characterizing our local galactic environment during solar system formation. These isotopic signatures provide traces of galactic chemical evolution operating over timescales that span significant fractions of cosmic history. Noble gas emission, detected through far ultraviolet spectroscopy, reveals the presence of helium, neon, and argon isotopes that escape detection during earlier phases of the comet's approach. These noble gases, chemically inert under most conditions, preserve isotopic ratios that directly reflect nucleosynthesis processes in their stellar sources, the 3 He/4. He ratio may differ dramatically from solar wind values, while neon isotope ratios could reveal processing through cosmic ray spallation during the comet's interstellar journey. Organic molecular emission begins revealing the presence of amino acid precursors and other prebiotic compounds that may have formed through interstellar chemistry processes operating under conditions unlike any found in our solar system. Glycine, the simplest amino acid, and more complex organic molecules containing nitrogen and sulfur functional groups create emission features that require sophisticated chemical models to interpret. These molecules represent potential building blocks for biological systems, suggesting that the universe's inventory of prebiotic chemistry extends far beyond what Earth's evolution has explored. As the spectroscopic analysis of 3 I/Atlas continues revealing molecular mysteries encoded in wavelengths of light that carry information across millions of years and countless light years of space, astronomers recognize that this interstellar visitor provides an unprecedented library of cosmic chemistry. Each photon absorbed and re-emitted by exotic molecules carries within its energy the signatures of stellar nucleosynthesis, interstellar processing, and chemical evolution operating on scales that dwarf terrestrial experience, offering glimpses into the vast molecular diversity that exists in the universe beyond our familiar solar system boundaries. At 2 astronomical units from the Sun, where solar heating reaches intensities comparable to those experienced by objects in the asteroid belt, 3 I/Atlas begins exhibiting outgassing behaviors that challenge every theoretical model developed to explain cometary activity. The jets of sublimating material that should emerge symmetrically from solar-heated regions instead follow directional patterns that suggest internal structure and volatile distributions shaped by processes unknown in solar system objects, creating activity patterns that appear to operate independently of external energy input. The classical model of cometary outgassing assumes that solar radiation penetrates a few centimeters into the nucleus surface, creating a subsurface sublimation zone where vapor pressure builds until expanding gases escape through surface fractures and pores. This model successfully explains the behavior of dozens of comets originating in our solar system's Oort cloud and Kuiper belt, their activity correlating predictably with heliocentric distance and solar illumination geometry according to well-established thermodynamic principles. 3 I/Atlas refuses to conform to these patterns. Its jets appear and disappear on timescales measured in hours rather than the days or weeks expected from thermal diffusion processes within comet nuclei. The directional preference of these jets shows weak correlation with the subsolar point, suggesting that volatile reservoirs exist in orientations determined by the comet's formation and processing history rather than by current solar heating patterns. Dr. Lisa Rodriguez analyzes high-resolution images that reveal jets emerging from regions of the nucleus that should remain in shadow according to the comet's rotational state and solar illumination geometry. These shadow-side jets challenge fundamental assumptions about the energy sources driving cometary activity, suggesting either that internal heat sources contribute to sublimation or that volatile transport mechanisms operate through pathways more complex than simple thermal diffusion from heated surface regions. The gas production rates measured through spectroscopic monitoring exhibit periodicities that correlate with the comet's rotation but include harmonic components that suggest asymmetric mass distribution or variable volatile concentrations across the nucleus surface. Standard models assume approximately uniform composition for comet nuclei, with regional variations smoothed by impact gardening and thermal processing over billions of years. The harmonic structure in 3I/8's outgassing suggests compositional heterogeneities that preserve their spatial organization throughout its interstellar journey. Dust-to-gas ratios in the expanding coma differ significantly from values typical of solar system comets, with dust production rates that appear enhanced relative to gas sublimation. This anomalous ratio suggests either that dust grains remain more weakly bound within the comet's matrix, or that gas production occurs through processes that do not efficiently entrain solid particles. The dust component exhibits size distributions that peak at larger particle sizes than those found in typical cometary comae, possibly reflecting aggregation processes that operated during the comet's formation in interstellar environments. Sublimation-driven spin changes, detectable through variations in the comet's light curve periodicity, indicate that outgassing creates torques around the nucleus center of mass that differ from predictions based on symmetric volatile distribution models. The comet's rotation period appears to be lengthening as outgassing removes angular momentum through preferential volatile loss from specific surface regions. These rotational changes suggest that 3I/Atlas may undergo dramatic spin state evolution as it approaches perihelion, potentially transitioning to chaotic tumbling motion. The coma morphology revealed through imaging at multiple wavelengths exhibits structure that persists far longer than standard expansion and dissipation models predict. Spiral patterns and shell-like features remain visible at distances exceeding 100,000 kilometers from the nucleus, suggesting that gas and dust particles maintain organized motion patterns that resist disruption by solar wind and radiation pressure. These persistent structures may result from magnetic field interactions or collective behavior in the expanding particle population. Temperature measurements of dust particles within the coma reveal thermal properties that differ from those of typical solar system materials. The particles appear to heat more slowly and cool more rapidly than expected for silicate or carbonaceous compositions, suggesting mineral structures or surface properties that reflect formation under interstellar conditions. Some particles exhibit temperatures that exceed thermal equilibrium values, possibly indicating internal heat sources related to radioactive decay or chemical reactions activated by solar heating. The comet's dust tail development follows evolutionary patterns that deviate from classical models based on radiation pressure acting on particles released from the nucleus. The tail exhibits brightness variations and morphological changes that correlate weakly with changes in dust production rates, suggesting that particle interactions within the tail create collective behaviors that standard models cannot predict. Electromagnetic effects or chemical processing may modify particle properties during their journey anti-sunward from the nucleus. Volatile species abundance ratios in the outgassing reveal chemical signatures that require revision of standard cometary composition models. The water-to-carbon monoxide ratio remains lower than typical solar system values even as solar heating increases, while nitrogen-bearing compounds appear in abundances that exceed predictions based on solar nebula chemistry. These abundance anomalies may reflect equilibrium condensation under interstellar pressure and temperature conditions that differ from those characterizing solar system formation. Internal pressure calculations suggest that expanding gases within the comet nucleus create stress fields that exceed the tensile strength of typical cometary materials. Yet 3I/Atlas maintains structural integrity without exhibiting the fragmentation events that destroy many comets during their first solar system passage. This mechanical stability may result from internal architecture developed during interstellar processing, possibly involving ice-dust matrices with strength properties unlike those found in solar system objects. The development of the hydrogen coma, created by photodissociation of water vapor in solar ultraviolet radiation, produces spatial distributions that extend farther from the nucleus than theoretical models predict. This extended hydrogen envelope suggests either enhanced water production rates or transport mechanisms that carry neutral hydrogen atoms to larger distances before ionization and pickup by solar wind removes them from the coma. The hydrogen distribution asymmetries correlate with the comet's orbital motion in ways that suggest interaction with interplanetary magnetic fields. Plasma interactions between the solar wind and ionized coma gases create electromagnetic signatures that differ from those observed around typical comets. The induced magnetic field patterns exhibit asymmetries that suggest non-uniform electrical conductivity within the coma or magnetic field perturbations created by charged particles with velocity distributions unlike those found around solar system comets. These electromagnetic anomalies may result from the comet's unique charge distribution or magnetic properties acquired during its interstellar journey. As 3I/Atlas continues its approach toward perihelion, exhibiting outgassing patterns that challenge theoretical understanding while maintaining structural integrity through processes unknown in solar system comets. Astronomers recognize that this interstellar visitor operates according to physical principles that extend beyond current knowledge. The jets of exotic gases and dust particles streaming from ancient ice carry within their dynamics the suggestion that cometary physics, like cometary chemistry, requires fundamental revision to accommodate objects whose origins lie in the vast spaces between stars, where matter and energy express themselves through mechanisms that Earth-based science is only beginning to discover, in the quantum vacuum that surrounds our solar system, where virtual particles flicker in and out of existence on timescales shorter than light can cross atomic nuclei. Physicists contemplate whether the trajectory anomalies exhibited by 3I/Atlas might represent the first astronomical detection of dark matter's gravitational influence on individual objects. This invisible substance, comprising approximately 27% of the universe's total mass energy, yet interacting with ordinary matter only through gravity, remains one of the most profound mysteries confronting modern cosmology and particle physics. The standard model of particle physics, despite its extraordinary success in describing electromagnetic, weak, and strong nuclear forces, provides no candidate particles with the properties required to explain dark matter's gravitational effects on galactic and cosmological scales. Weakly interacting massive particles, WIMPs, axions, sterile neutrinos, and primordial black holes represent leading theoretical candidates, each predicting different signatures for how dark matter should influence the motion of objects traveling through regions where its density varies significantly. 3I/Atlas's interstellar journey has carried it through galactic environments where dark matter density may differ substantially from the approximately 0.3 GeV per cubic centimeter estimated for our local neighborhood. Dense dark matter subhalos, predicted by cosmological N-body simulations to exist throughout galactic disks, could create gravitational potential wells that influence the trajectories of passing objects while remaining invisible to electromagnetic observations. The comet's trajectory anomalies could provide the first direct evidence of such structures. Dr. Chen Wei, a theoretical physicist specializing in dark matter phenomenology, develops models for how different dark matter candidates should affect interstellar object trajectories over millions of years of galactic travel. The calculations require sophisticated numerical integration techniques that account for both the smooth dark matter component associated with galactic structure and the clumpy subhalo population that emerges from hierarchical structure formation in cold dark matter cosmologies. Gravitational microlensing effects from dark matter concentrations could create temporary trajectory modifications that accumulate over the vast timescales characteristic of interstellar travel. These effects, individually too small to detect through direct observation, might produce measurable cumulative changes in orbital elements when integrated over millions of years. The stochastic nature of such interactions would create trajectory modifications that appear random, but exhibit statistical properties that could distinguish dark matter effects from other gravitational perturbations. The possibility that dark matter exhibits self-interactions through forces beyond standard gravity provides another framework for understanding 3I/Atlas's anomalous behavior. Self-interacting dark matter models, developed to address discrepancies between observed and simulated galactic structure on small scales, predict that dark matter particles could scatter elastically or exchange momentum through dark sector forces that operate independently of ordinary matter interactions. If dark matter particles carry charges under hidden gauge symmetries, they could create long-range forces that influence the motion of objects containing dark matter components, while ordinary matter remains largely immune to such forces. Composite objects that incorporated dark matter during their formation in dense molecular clouds could experience accelerations that depend on their dark matter content rather than their ordinary matter mass. This scenario would predict trajectory anomalies that correlate with formation environment rather than current position. Axion dark matter, comprising ultralight scalar fields that oscillate coherently across astronomical scales, could create time-varying gravitational potentials that influence object trajectories through mechanisms analogous to tidal forces. The Compton wavelength of ultralight axions approaches parsec scales, creating gravitational field oscillations that could produce periodic trajectory modifications with characteristic frequencies determined by the axion mass. 3. I/Atlas's trajectory. Anomalies might preserve signatures of such oscillations accumulated during its interstellar journey. The dark matter velocity distribution in our local galactic neighborhood exhibits structure related to the merger history of the Milky Way and the phase space distribution of dark matter, halos, and subhalos. Recent simulations suggest that dark matter streams from disrupted satellite galaxies could create preferred directions for dark matter particle velocities that differ from the smooth halo models typically assumed for direct detection experiments. Interstellar objects like 3I/Atlas could probe this velocity structure through gravitational interactions that depend on relative velocities between the comet and dark matter particle populations. Primordial black holes, if they comprise a significant fraction of dark matter, could create gravitational perturbations that affect interstellar object trajectories through classical general relativistic effects rather than exotic particle interactions. These compact objects, with masses potentially ranging from asteroid scales to stellar masses, would create point source gravitational fields that could deflect passing objects through close encounters. The stochastic nature of such encounters would produce trajectory modifications similar to those observed for 3I/Atlas. Dark matter interactions with ordinary matter through nuclear recoils, while suppressed relative to gravitational interactions, could produce measurable effects for objects that have spent millions of years traveling through regions of enhanced dark matter density. The momentum transfer from dark matter particle collisions with atomic nuclei in comet materials would create tiny accelerations that accumulate over cosmological timescales, potentially producing the kinds of systematic trajectory changes observed for 3I/Atlas. Modified gravity theories, developed as alternatives to dark matter for explaining galactic dynamics, predict different signatures for how gravitational forces should deviate from general relativity in the weak field regime characteristic of galaxy outskirts and interstellar space. Emergent gravity, modified Newtonian dynamics, MOND, and extra-dimensional models each make specific predictions about trajectory modifications that should affect objects traveling through regions where gravitational acceleration falls below critical threshold values. The scalar tensor gravity theories that arise naturally in string theory cosmology predict that gravitational coupling strength could vary with environment in ways that affect object trajectories differently depending on their composition and formation history. Objects formed in different gravitational environments could exhibit different responses to local gravitational fields, creating trajectory anomalies that depend on formation conditions rather than current position. This framework could explain why interstellar objects exhibit different gravitational behavior than solar system bodies. Quantum gravitational effects, typically negligible for macroscopic objects under ordinary conditions, might become relevant for understanding the motion of objects that have traveled cosmological distances through the quantum vacuum of space. Virtual particle interactions with massive objects could create tiny but persistent forces that accumulate over the vast timescales characteristic of interstellar travel, producing measurable trajectory modifications that depend on object composition and environmental history. The cosmological constant problem, which highlights the enormous discrepancy between observed vacuum energy density and theoretical predictions from quantum field theory, suggests that our understanding of space-time at the largest scales remains incomplete. 3. I/Atlas's trajectory. Anomalies could provide insights into how vacuum energy interacts with matter over cosmological timescales, potentially revealing signatures of dark energy's influence on individual object motion through mechanisms that operate below current observational thresholds for local measurements. As theoretical physicists continue developing models to explain how dark matter might influence the trajectory of an interstellar visitor. 3. I/Atlas moves through our solar system, carrying within its orbital elements potential evidence for physics beyond the standard model. The subtle accelerations that challenge celestial mechanics may represent humanity's first direct encounter with the dark sector of the universe, encoded in the patient drift of ice and rock through the quantum vacuum where virtual particles dance just beyond the threshold of measurable existence. Where the solar wind meets 3. I/Atlas's expanding coma. Electromagnetic interactions create a complex plasma environment that reveals magnetic properties acquired during the comet's millions of years journey through interstellar magnetic fields. The solar wind, that continuous stream of charged particles flowing outward from our sun at velocities approaching 400 kilometers per second, encounters neutral gas expanding from the comet's nucleus and creates boundary layers where electromagnetic forces dominate over simple gravitational dynamics. The induced magnetosphere that forms around active comets results from the interaction between solar wind magnetic fields and the conducting plasma created by ionization of cometary gases. For typical solar system comets, these interactions follow well-understood magnetohydrodynamic principles, creating bow shocks, magnetic field draping, and plasma tail formation that spacecraft missions have observed and characterized in detail. 3. I/Atlas exhibits electromagnetic signatures that deviate from these established patterns in ways that suggest magnetic properties unlike any solar system object. Dr. Sarah Mitchell analyzes magnetic field measurements from deep space monitoring stations that detect perturbations in the interplanetary magnetic field as 3 I/Atlas approaches. The comet appears to carry with it magnetic field enhancements that exceed predictions based on induced magnetosphere models, suggesting either that the nucleus contains materials with unusual magnetic properties or that magnetic fields became frozen into the comet's structure during its formation in magnetically active interstellar environments. Ferromagnetic minerals within the comet nucleus, magnetized during encounters with interstellar magnetic fields over millions of years, could create permanent magnetic dipoles that interact with solar system electromagnetic environments in unprecedented ways. Magnetite, pyrrhotite, and other iron-bearing minerals that commonly occur in meteoritic materials can acquire and retain magnetization under appropriate field conditions, creating magnetic moments that persist for geological timescales in the absence of demagnetizing influences. The interstellar magnetic field environment through which 3 I/Atlas traveled during its journey to our solar system differs dramatically from the relatively benign electromagnetic conditions that characterize the solar wind and planetary magnetospheres, molecular clouds, supernova shock fronts, and stellar wind boundaries create magnetic field strengths that can exceed interplanetary values by orders of magnitude. providing opportunities for magnetic field freezing and particle acceleration that operate under conditions impossible to study through direct observation. Alpha wave interactions between the comet's magnetic field and solar wind create electromagnetic signatures detectable through radio astronomy observations. These magnetohydrodynamic waves, propagating along magnetic field lines at velocities determined by field strength and plasma density, carry information about magnetic field configurations and plasma parameters throughout the interaction region. The wave characteristics observed around 3I/Atlas suggest magnetic field geometries that differ from those typical of solar system objects. Charge separation processes within the expanding coma create electric fields that accelerate ions and electrons to different velocities, generating electromagnetic radiation through synchrotron and cyclotron mechanisms. The frequency spectrum and polarization properties of this emission depend critically on magnetic field strength and particle energy distributions, providing remote sensing capabilities for diagnosing plasma conditions that cannot be measured through direct spacecraft encounters. The pickup ion population created by ionization of neutral cometary gases and subsequent acceleration by solar wind electric fields exhibits velocity distributions that suggest magnetic field interactions more complex than those observed around typical comets. These newly created ions, initially at rest in the comet's reference frame, should achieve characteristic energies determined by solar wind speed and magnetic field strength through well-understood plasma acceleration mechanisms. The energy spectra observed for 3I/Atlas's pickup ions indicate additional acceleration processes that may result from magnetic reconnection or wave-particle interactions. Magnetic field line reconnection events, where oppositely directed magnetic fields annihilate and release stored magnetic energy as particle kinetic energy, may occur preferentially in regions where the comet's intrinsic magnetic field encounters solar wind, magnetic fields with different orientations. These reconnection sites create localized acceleration regions that produce high-energy particle populations and electromagnetic emission signatures that differ from the steady-state plasma interactions typical of magnetically passive comets. The plasma instabilities that develop in the comet's wake, downstream from the nucleus in the anti-solar direction, exhibit growth rates and wavelength characteristics that suggest magnetic field configurations unlike those observed around solar system comets. Two-stream instabilities, driven by relative velocity differences between different ion populations, and magnetic field-driven instabilities create turbulent plasma environments that affect particle transport and electromagnetic emission throughout the comet's extended magnetosphere. Dust grain charging processes within the coma occur through complex interactions between photoelectron emission, secondary electron emission from particle impacts, and current collection from the ambient plasma. The equilibrium electric potential achieved by dust particles depends on their size, composition, and local plasma environment in ways that affect their subsequent motion through electromagnetic forces that can exceed gravitational and radiation pressure effects for small particles. The magnetic shielding effect created by the comet's interaction with solar wind may protect certain regions of the nucleus from energetic particle bombardment, while exposing other regions to enhanced particle fluxes focused by magnetic field convergence. This asymmetric shielding could create compositional gradients across the nucleus surface that reflect magnetic field interactions accumulated over the comet's interstellar journey and current solar system passage. Magnetic field amplification through turbulent dynamo processes in the conducting plasma surrounding the nucleus could enhance local magnetic field strengths far above solar wind values, creating environments where magnetic pressure dominates over thermal pressure in determining plasma behavior. These amplified field regions would affect particle trajectories, plasma wave propagation, and electromagnetic emission characteristics in ways that standard magnetohydrodynamic models struggle to predict accurately. The temporal evolution of magnetic field interactions as 3Y/Atlas approaches perihelion reflects the changing balance between intrinsic magnetic properties, induced electromagnetic effects, and external solar wind driving. Magnetic field measurements obtained at different phases of the comet's approach provide insights into how magnetic properties developed during interstellar travel interact with solar system electromagnetic environments to create the complex magnetic signatures observed around this visitor from the void. Plasma heating mechanisms operating within the comet's magnetosphere create temperature distributions that exceed thermal equilibrium values predicted by standard models. Ion temperatures derived from spectroscopic Doppler broadening and electron temperatures inferred from emission line ratios both indicate plasma heating rates that suggest magnetic field interactions contribute significantly to energy deposition within the expanding coma. Through mechanisms that may include magnetic reconnection, wave dissipation, and current sheet formation. As 3I/Atlas continues its passage through the inner solar system, carrying with it magnetic memories of interstellar environments and creating electromagnetic interactions that challenge theoretical understanding. Astronomers recognize that this visitor from beyond the heliopause provides unprecedented opportunities to study plasma physics operating under conditions that bridge interstellar and solar system environments. The magnetic signatures embedded within ancient ice, activated by solar system electromagnetic fields, offer glimpses into the magnetic architecture of interstellar space that Earth-based observations can measure only through the average signatures of distant astronomical sources. At 1 astronomical unit from the Sun, Earth's orbital distance, where solar energy flux reaches the familiar 1,361 watts per square meter that drives our planet's climate system, 3I/Atlas begins exhibiting subtle course corrections that challenge the deterministic principles underlying celestial mechanics. These minute trajectory adjustments, detectable only through the most precise astrometric measurements accumulated over months of observation, suggest that the comet experiences forces beyond those accounted for in standard gravitational models, as if the visitor from interstellar space operates according to navigational principles unknown in our solar system. The phenomenon manifests most clearly in orbital residuals, the tiny differences between where mathematical models predict the comet should appear and where telescopes actually observe it. For typical solar system objects, these residuals decrease steadily as observational data accumulates and orbital solutions converge toward increasingly accurate representations of gravitational reality. 3I/Atlas exhibits residuals that persist at levels exceeding observational uncertainty, suggesting systematic effects that standard perturbation theory cannot explain. Dr. Carlos Mendez analyzes decades of experience in precision orbit determination as he watches his most sophisticated orbital integration software produce prediction errors that grow rather than shrink with additional observations. The comet's position measurements, obtained from multiple observatories using identical reduction procedures, consistently disagree with theoretical predictions by amounts that suggest either revolutionary discoveries in gravitational physics or the operation of forces that current models do not recognize. The trajectory modifications appear correlated with solar activity cycles, suggesting that electromagnetic interactions between the comet and solar wind may create forces that accumulate over time to produce measurable orbital changes. Solar magnetic field variations, driven by the Sun's 11-year activity cycle, modulate the electromagnetic environment throughout the solar system in ways that could affect objects with unusual magnetic or electrical properties acquired during interstellar travel. Sublimation-driven outgassing should create predictable, non-gravitational accelerations as expanding gases produce rocket-like thrust that modifies orbital elements according to well-established relationships between gas production rates, nucleus rotation, and solar illumination geometry. The accelerations exhibited by 3I/Atlas exceed those predicted by outgassing models and exhibit directional preferences that correlate weakly with solar heating patterns, suggesting additional force mechanisms that operate independently of thermal-driven sublimation. The Yarkovsky effect, a subtle recoil force created when rotating objects radiate thermal energy into space with preferential directionality, should produce orbital evolution that correlates with the comet's thermal properties and rotation state. For 3I/Atlas, thermal infrared observations suggest surface temperature distributions that should create Yarkovsky accelerations in specific directions. Yet the observed trajectory changes follow patterns that match theoretical predictions only approximately, with systematic deviations that accumulate over time. Radiation pressure from solar photons, while tiny for massive objects, could create measurable acceleration for a comet with unusual albedo properties or asymmetric mass distribution. The observed trajectory corrections suggest acceleration components that vary with solar distance in ways consistent with radiation pressure effects, but with magnitudes that exceed predictions based on the comet's measured optical properties and estimated mass. These discrepancies may indicate surface composition or structure that differs significantly from typical cometary materials. General relativistic effects, normally negligible for solar system dynamics except in the innermost regions near the Sun, could become detectable for objects with trajectories that sample a wide range of gravitational potential differences. 3I/Atlas's hyperbolic orbit carries it through regions where space-time curvature varies significantly, creating opportunities for relativistic corrections to become measurable through accumulated effects over its entire solar system passage. Gravitational wave interactions, while extraordinarily weak for individual objects, could produce cumulative effects that become detectable for bodies that have traveled cosmological distances through the universe's gravitational wave background. The comet's interstellar journey exposed it to gravitational radiation from sources throughout our local galactic environment, potentially creating trajectory modifications that preserve information about the gravitational wave environment in regions of space that Earth-based detectors cannot directly observe. The solar wind dynamic pressure, varying with solar activity and heliocentric distance, creates a drag-like effect on objects moving through the charged particle environment of interplanetary space. For electrically neutral objects, this drag remains negligible, but 3I/Atlas may carry electric charge accumulated during its journey through interstellar space, creating electromagnetic coupling with solar wind that produces measurable acceleration. The magnitude and direction of these forces would depend on the comet's charge distribution and the local solar wind magnetic field orientation. Magnetic field interactions between any permanent magnetization within the comet nucleus and the solar wind's embedded magnetic field could create Lorentz forces that modify the trajectory in ways that depend on the relative orientation between the comet's magnetic dipole and the interplanetary magnetic field. These electromagnetic forces, while small compared to gravitational effects, could accumulate measurable changes over the months-long duration of the comet's solar system passage. Frame dragging effects from the Sun's rotation, a general relativistic phenomenon where rotating massive objects drag space-time around themselves, could create trajectory perturbations that become detectable for objects following highly eccentric orbits that sample different regions of the solar gravitational field. The lens-thirring precession associated with frame dragging remains unmeasurably small for typical solar system objects, but might become detectable for interstellar visitors whose trajectories carry them through regions where gravitational field gradients are steep. Dark matter interactions, if they operate through mechanisms beyond pure gravitational attraction, could create forces that affect the motion of objects that incorporated dark matter components during their formation in dense molecular clouds. Self-interacting dark matter models predict that dark sector particles could exchange momentum through hidden forces that influence the trajectories of composite objects containing both ordinary and dark matter components in proportions that reflect their formation environment. Quantum vacuum effects, while typically irrelevant for macroscopic objects, could become detectable for bodies that have spent eons traveling through the quantum vacuum of interstellar space. Virtual particle interactions with massive objects could create tiny but persistent forces that accumulate over cosmological timescales, producing trajectory modifications that depend on object composition and environmental history in ways that classical physics cannot predict. Pioneer anomaly-type effects, similar to the unexplained acceleration observed for the Pioneer spacecraft in the outer solar system, could affect 3I/Atlas through mechanisms that remain poorly understood despite decades of investigation. These anomalous accelerations, possibly related to asymmetric thermal radiation or systematic errors in deep space navigation, suggest that our understanding of forces acting on objects in the outer solar system may remain incomplete. Tidal effects from galactic structure, while negligible for solar system objects over human timescales, could produce measurable trajectory modifications for bodies that have traveled interstellar distances and retained gravitational memories of encounters with massive structures in our local galactic environment. The differential gravitational field created by stellar clusters, molecular clouds, and dark matter concentrations could leave signatures in object trajectories that persist long after the original encounters. Modified gravity theories that predict deviations from general relativity in weak gravitational fields could create trajectory modifications that become detectable only for objects sampling the full range of gravitational environments from interstellar space to the inner solar system. Scalar tensor theories, extra-dimensional models, and emergent gravity frameworks each predict specific signatures for how gravitational forces should vary with field strength and environmental conditions. Internal structural changes within the comet nucleus, driven by thermal stress, sublimation-induced mass redistribution, or phase transitions in exotic ice compositions, could alter the object's mass distribution in ways that affect its response to external forces. These structural evolution processes could create time-varying changes in the comet's gravitational interactions and rotational dynamics that produce apparent trajectory anomalies. Solar oblateness effects, resulting from the sun's rotation-induced flattening, create gravitational field asymmetries that affect orbital evolution for objects following highly eccentric trajectories. The sun's quadrupole gravitational moment produces perihelion precession and other orbital changes that could contribute to the trajectory modifications observed for 3I/Atlas, though the predicted magnitudes remain smaller than the observed anomalies. Atmospheric drag from the extended solar atmosphere, including coronal mass ejections and enhanced particle densities during solar maximum conditions, could create velocity-dependent forces that affect the trajectories of objects passing through the inner solar system. While the solar atmosphere remains extremely tenuous compared to planetary atmospheres, its effects could become detectable for objects with unusual surface properties or charge distributions. Interplanetary dust interactions, including momentum transfer from microscopic particle impacts and electromagnetic scattering from charged dust grains, could create cumulative forces that modify object trajectories over time. The zodiacal dust environment varies with heliocentric distance and ecliptic latitude in ways that could produce systematic acceleration components correlated with orbital geometry, as 3I/Atlas continues its passage through the inner solar system, exhibiting trajectory modifications that resist explanation through conventional celestial mechanics. Astronomers confront the possibility that this visitor from interstellar space operates according to physical principles that extend beyond current theoretical frameworks. The subtle course corrections, detectable only through humanity's most precise measurement techniques, may represent the first observational evidence of new physics operating on scales and in environments that Earth-based science has never directly explored. The comet moves through familiar solar system space with the quiet persistence of a natural experiment that challenges the boundaries of human knowledge. Its trajectory, carrying encoded within subtle deviations from theoretical predictions, The suggestion that the universe operates according to rules more complex and beautiful than our current understanding can encompass. In the mathematical language of orbital mechanics, written across the sky in the patient motion of ice and rock, 3I/Atlas inscribes corrections to the equations that govern motion through space and time. Beyond the orbit of Mars, where solar heating weakens and the ancient ice within 3Y/Atlas begins its return to the dormant state that characterized millions of years of interstellar travel. The comet starts its patient withdrawal from our sun's influence and back toward the infinite darkness between stars. The outgassing that briefly transformed this visitor into an active comet gradually subsides as solar energy flux falls below the threshold required to maintain significant sublimation, leaving behind a nucleus whose surface has been permanently altered by its brief encounter with stellar warmth. The trajectory that will carry 3I/Atlas away from our solar system forever exhibits the mathematical elegance of a hyperbolic orbit, its eccentricity greater than unity, ensuring that gravitational capture by our sun remains impossible regardless of future perturbations from planetary encounters. Unlike the elliptical paths that eternally return solar system objects to their starting points, this escape trajectory extends toward regions of space that our telescopes cannot observe and our theories can barely imagine. Dr. Elena Vasquez performs final orbital integrations as the comet's trajectory becomes increasingly well determined with each passing week of observations. The mathematical models that struggled with anomalous accelerations and forbidden zone instabilities during the approach phase now converge toward solutions that predict the comet's exit from our solar system with precision measured in arc-seconds per century. Yet even these final calculations contain residual uncertainties that suggest the influence of forces or effects that standard celestial mechanics cannot fully capture. The comet's nuclear surface, modified by its encounter with solar radiation and solar wind particles, will carry into interstellar space a record of conditions within our solar system encoded in chemical and physical changes that occurred during its brief period of activity. Radiation damage from solar ultraviolet exposure, implanted ions from solar wind bombardment, and compositional changes from preferential volatile loss create a thin layer of processed material that preserves information about our sun's electromagnetic environment. Solar wind interactions have implanted hydrogen, helium, and heavier ions into the comet's surface layers, creating isotopic signatures that will persist throughout its journey to other stellar systems. These implanted solar particles, trapped within crystal lattices and grain boundaries, represent samples of our sun that will travel with 3I/Atlas across galactic distances, potentially providing information about solar composition to civilizations that may encounter this visitor millions of years in the future. The dust tail that formed during the comet's approach to perihelion will gradually disperse as particles achieve independent orbits around the sun or escape the solar system entirely. Some of this dust, carrying isotopic and chemical signatures of interstellar origin, will eventually be incorporated into asteroids, meteoroids, and planetary atmospheres throughout our solar system, contaminating the local environment with materials that originated in entirely different stellar neighborhoods. Orbital mechanics calculations extending millions of years into the future suggest that 3I/Atlas will encounter the gravitational influence of nearby stars as it travels through our local galactic neighborhood. Alpha Centauri, Barnard's star, and other members of the local stellar association will create perturbations that gradually modify the comet's trajectory, potentially directing it toward regions of the galaxy where stellar densities and chemical compositions differ from those that characterized its formation environment. The velocity vector with which 3I/Atlas exits our solar system carries encoded within its direction and magnitude the accumulated gravitational influences of every massive object it encountered during its passage through our stellar system. Jupiter's enormous gravitational field, Saturn's ring system, and even the subtle influences of terrestrial planets have contributed infinitesimal modifications to the comet's final departure trajectory, creating a mathematical fingerprint of our solar system's mass distribution. As the comet recedes beyond the orbit of Jupiter, its apparent brightness fades according to the inverse square law until only the largest ground-based telescopes can detect its reflected sunlight against the cosmic background radiation. The final observations will occur when 3I/Atlas reaches distances comparable to Saturn's orbit, beyond which even the most sensitive instruments will lose track of this visitor as it fades into the infrared darkness of deep space. The information carried within 3I/Atlas's structure represents a unique form of galactic communication, encoding within solid matter the chemical signatures of stellar nucleosynthesis, molecular cloud processing, and interstellar environment conditions that operated millions of years ago in regions of space separated from our solar system by hundreds or thousands of light years. This information, preserved in crystalline ices and mineral grains, travels at modest velocities between stellar systems, creating a slow but persistent exchange of material and information across galactic distances. Gravitational slingshot effects from close encounters with massive planets have increased the comet's escape velocity relative to our solar system, ensuring that its journey toward other stars will require less time than its approach from interstellar space. The additional kinetic energy provided by planetary gravity assists will carry 3I/Atlas toward its next stellar encounter with enhanced speed that could reduce transit times by tens of thousands of years. The comet's magnetic properties, modified by interactions with solar system electromagnetic fields, will influence its passage through interstellar magnetic field structures during its onward journey. Remnant magnetization acquired through solar wind interactions and thermal cycling may create magnetic dipole moments that interact with galactic magnetic fields in ways that produce subtle trajectory modifications over cosmological timescales. Future stellar encounters will subject 3I/Atlas to gravitational and electromagnetic environments that may differ dramatically from those characterizing our solar system. Red dwarf stars with powerful magnetic fields and frequent flare activity, binary systems with complex gravitational dynamics, and evolved stars with intense stellar winds will create conditions that could further modify the comet's composition and structure through processes unknown in our relatively benign stellar neighborhood. The possibility that 3I/Atlas will eventually be captured into orbit around another star depends on the specific details of future gravitational encounters and the comet's velocity at the time of closest approach. Capture. Probability calculations suggest that interstellar objects like this visitor have extremely low likelihood of achieving bound orbits around new stellar systems, making their role primarily that of transient messengers carrying information between isolated stellar neighborhoods. Statistical analysis of galactic dynamics suggests that 3I/Atlas may encounter thousands of stellar systems during its journey around our galaxy's disk, each encounter providing opportunities for gravitational perturbations that gradually modify its orbital parameters and chemical composition. The cumulative effects of such encounters over hundreds of millions of years could transport the comet across significant fractions of galactic radius, creating opportunities for sampling diverse stellar environments and chemical compositions. The comet's eventual fate remains uncertain across the vast timescales characteristic of galactic evolution. Stellar encounters, galactic tidal effects, collision with interstellar matter, or incorporation into star-forming regions could terminate its existence as a discrete object, redistributing its constituent atoms and molecules into the interstellar medium, where they may eventually participate in the formation of new stellar systems and planetary environments. As 3I/Atlas fades from telescopic visibility and begins its return to the patient darkness between stars, it carries with it not only the chemical memories of its formation in ancient molecular clouds, but also the gravitational and electromagnetic signatures of its encounter with our solar system. The visitor from the void returns to the infinite, bearing within its ancient ice and rock a record of our sun's influence that will persist across the cosmic dark until chance or destiny brings it within the gravitational embrace of distant stars whose light has not yet reached Earth's telescopes. In the deep observatories where theoretical astrophysicists gather to reconcile observation with mathematical law, the equations that govern celestial motion undergo quiet revision as 3I/Atlas recedes beyond the reach of human instruments. The models that successfully predicted planetary positions for centuries, that guided spacecraft across billion-kilometer trajectories with meter-scale precision, that mapped the gravitational architecture of our entire solar system, now acknowledge their limitations through marginal corrections and uncertainty parameters that reflect encounters with physics operating beyond their foundational assumptions. The orbital integration software that struggled with forbidden zones and mathematical instabilities throughout the comet's approach now incorporates empirical corrections that allow stable trajectory calculations at the cost of theoretical elegance. These modifications, derived from the accumulated residuals between observation and prediction, represent phenomenological patches to gravitational theory rather than fundamental understanding of the physical processes that created the anomalous behavior. Dr. Sarah Chen archives the final observational data as 3I/Atlas fades beyond detection limits, recognizing that this dataset represents humanity's most complete record of how an interstellar object behaves during passage through our solar system. The measurements, extending from first detection at 30 astronomical units to final observations at 12 astronomical units outbound, document trajectory anomalies, spectroscopic signatures, and electromagnetic interactions that challenge theoretical frameworks across multiple branches of physics. Celestial mechanics textbooks will require new chapters discussing the behavior of hyperbolic objects with interstellar origins. Acknowledging that gravitational theory developed for solar system applications may not extend directly to objects whose formation and processing history occurred under fundamentally different conditions, the mathematical formalism remains valid. But the assumption of universal applicability requires modification to accommodate phenomena observed in visitors from beyond the heliopause. The comet's chemical signatures, preserved in spectroscopic databases and isotopic measurements, provide baseline data for interpreting future interstellar visitors and developing models of molecular cloud chemistry that operate under conditions never directly observed from Earth-based platforms. These measurements represent ground truth for theoretical models of interstellar processing, chemical evolution, and the transport of matter between stellar systems across galactic distances. Modified gravity theories gain new observational constraints from 3I/Atlas's trajectory data, with some theoretical frameworks ruled out by the specific pattern of anomalous accelerations, while others receive modest support from correlations between gravitational environment and observed deviations. The comet's passage through regions of varying gravitational field strength provides a natural laboratory for testing alternatives to general relativity under conditions impossible to replicate through terrestrial experiments. Dark matter interaction models undergo refinement as theorists attempt to explain the comet's behavior through mechanisms involving hidden sector physics. Self-interacting dark matter, or gravitational effects from dark matter substructure. The trajectory anomalies provide upper limits on interaction cross-sections and lower limits on dark matter density variations that constrain theoretical models while opening new avenues for indirect dark matter detection through astronomical observations. Magnetohydrodynamic simulations of comet-solar-wind interactions incorporate new boundary conditions and material properties derived from 3I/Atlas electromagnetic signatures, improving theoretical understanding of how interstellar magnetic fields interact with solar system plasma environments. These enhanced models will prove crucial for interpreting future observations of interstellar objects and understanding the electromagnetic coupling between different astrophysical environments. Cometary outgassing models expand to include chemical species and physical processes unknown in solar system objects, accommodating exotic ice phases, unusual volatile compositions, and sublimation mechanisms that operate under conditions of extreme cold and low pressure. The theoretical framework for understanding cometary activity broadens to encompass formation environments characterized by interstellar chemistry and million-year processing timescales. Statistical models for the interstellar object population undergo revision based on 3I/Atlas's properties and behavior, with new estimates for the frequency of such visitors, their typical composition and size distributions, and the likelihood of detecting objects with observable anomalous behavior. These population models inform searches for additional interstellar objects and provide context for interpreting the significance of detected anomalies. Galactic chemical evolution models incorporate new constraints on isotopic ratios and molecular species abundances derived from detailed analysis of 3I/Atlas's composition, improving theoretical understanding of how stellar nucleosynthesis products mix and transport through the interstellar medium over cosmological timescales. The comet's chemical inventory provides snapshots of galactic chemical conditions that existed millions of years ago in regions separated from our solar system by vast distances. Orbital dynamics codes used for spacecraft navigation and asteroid impact assessment include new subroutines for handling objects with hyperbolic trajectories and anomalous acceleration components, ensuring that future interstellar visitors can be tracked with appropriate uncertainty estimates. Mission planning protocols incorporate lessons learned from 3I/Atlas's behavior, developing contingency procedures for encounters with objects that may not follow standard gravitational predictions. International space law frameworks begin considering regulatory approaches for objects originating beyond our solar system, addressing questions of scientific access, sample return missions, and potential biosafety protocols for materials that may have been exposed to biological processes operating under non-terrestrial conditions. The legal status of interstellar objects raises novel questions about sovereignty and scientific responsibility that existing treaties do not address. Astrobiology research programs expand to include study of complex organic molecules detected in interstellar objects, investigating whether chemical evolution in molecular cloud environments could produce prebiotic compounds that differ from those formed under solar system conditions. The organic inventory, carried by 3I/Atlas, provides new insights into the diversity of carbon chemistry that operates throughout the galaxy. Search strategies for additional interstellar objects incorporate lessons learned from 3I/Atlas's discovery and characterization, optimizing survey parameters for detecting faint objects with high relative velocities and unusual spectroscopic signatures. Improved detection capabilities ensure that future visitors will be identified earlier in their approach, allowing more comprehensive study of their properties and behavior. Theoretical frameworks for understanding the galactic environment expand to encompass the complex interactions between stellar systems, dark matter distributions, magnetic field structures, and the transport of solid objects across interstellar distances. 3I/Atlas's journey provides observational constraints on models of galactic structure and dynamics that operate on scales far exceeding direct astronomical observation. Machine learning algorithms trained on 3I/Atlas's observational data begin identifying patterns and correlations that human analysis overlooks, potentially revealing subtle signatures of new physics or previously unrecognized systematic effects. These artificial intelligence approaches complement traditional theoretical analysis by exploring high-dimensional parameter spaces that exceed human pattern recognition capabilities. As the scientific community continues analyzing the implications of humanity's encounter with this visitor from interstellar space, 3I/Atlas recedes into the cosmic dark, carrying with it the quiet satisfaction of having challenged human knowledge and forced recognition of how much remains unknown about the universe beyond our familiar solar system boundaries. The comet's legacy persists in modified equations, expanded theoretical frameworks, and the humbling recognition that objects formed under alien conditions may forever remain partially mysterious to Earth-based science. In observatories around the world, astronomers continue monitoring the sky for the next interstellar visitor, knowing now that such objects carry within their ancient ice and rock the potential to revolutionize understanding of physics, chemistry, and the vast cosmos that extends beyond our sun's protective influence. The models have been rewritten, but the universe continues to compose new problems in the mathematical languages that human knowledge has yet to learn, waiting patiently in the darkness between stars for the next messenger to arrive, bearing questions wrapped in the elegant simplicity of ice and stone drifting through the infinite. In the deep silence that follows mathematical revolution, where equations settle into new equilibrium configurations like sediment after turbulent flow. 3I/Atlas continues its patient journey towards stellar distances that dwarf human comprehension. The comet moves through space with the unhurried persistence of an object that has learned to navigate environments where time measures itself in millions of years and distance counts itself in units of light's long travel. The visitor from the void carries within its crystalline structure the accumulated influences of our solar system's gravitational embrace, Jupiter's massive pull recorded in subtle trajectory modifications, Saturn's rings encoded in magnetic field interactions, our sun's warmth preserved in surface chemistry, changes that will persist across cosmic distances. These solar system signatures join the chemical memories of ancient molecular clouds, stellar winds, and interstellar processing that preceded its arrival, creating a composite record of environments spanning significant fractions of galactic space and time. Behind it, 3I/Atlas leaves. The quiet suggestion that human knowledge operates within boundaries more modest than previously assumed. That the universe continues writing physics in languages Earth-based science has yet to learn to read. The mathematical models that guide spacecraft and predict celestial events acknowledge through marginal corrections and empirical adjustments that reality extends beyond theoretical grasp, that visitors from the deep spaces between stars carry with them reminders of cosmic humility. In the darkness ahead, where no telescope can follow and no equation can predict with certainty, the comet returns to the patient rhythm of interstellar travel, drifting through environments where matter exists in densities measured in atoms per cubic meter, where magnetic fields stretch across parsecs of space, where time and distance assume proportions that transform even the most fundamental physical processes into slow symphonies of cosmic evolution. The ancient ice sleeps once more, its brief awakening in solar warmth, now memory encoded in surface modifications and chemical alterations. The visitor settles into the eternal quiet of objects that have learned to count time in geological epochs and measure distance in the patient accumulation of light years. In the infinite darkness between worlds, 3I/Atlas continues its journey toward destinations that exist only in the statistical predictions of galactic dynamics and the mathematical poetry of orbital mechanics extended across cosmic scales. Sleep comes to matter as it has always come, gradually, inevitably, with the gentle persistence of entropy seeking its most probable configurations. In the deep cold where even molecular motion approaches stillness, where the cosmic microwave background provides the only warmth against absolute zero. Matter arranges itself according to the most fundamental physical laws and waits with infinite patience for the next gravitational disturbance to write new stories across the vast pages of space and time.